Oh no, it says it worked. All right, good deal. Well, it says we're live. So, all right, guys. Hello, everybody. This welcome to another Team Skeptic stream. Of course, we did think we were going to have issues because I was getting a live streaming not available message before I actually started. So I wasn't sure whether this was going to start or not, and it did. We actually have a flat earther that showed up tonight, so we should have a pretty good show for you, and we'll get into introducing her in one moment. First, I'd like to say hello to my partner in crime and my partner on this show, FTFE. How you doing tonight, sir?
Doing good, doing good. Looking forward to having a conversation about the shape of our Earth, where there isn't a debate. The Earth's not flat. You know how this works, guys. Rachie seems like a decent person. Interactions I've had with her in comments on Seek Truth, Speak Truth's channel. So she did make a video that I watched that was interesting. But let's see how it goes.
Yes, and Rachie, you are the guest of honor tonight, being that you're the person who's not normally here. How are you doing tonight, ma'am?
I'm all right, thank you very much. How about you?
No, I'm doing pretty good. I actually slept a lot yesterday, so I feel like completely refreshed. Ready to get into this conversation. Now, before we get started, I'm going to go ahead and cover all the super chats and our new member. We have Outlaw Jer, who's not really a new member. He's actually a returning member. I believe I saw in his in the beginning of the chat, he said that he had a new credit card, so it canceled his old membership, and he resubscribed. So thank you very much, Outlaw. I do appreciate it, and you know what we do, guys. Let me y'all are gonna have to share the emojis because I unfortunately can't do it right this second. But yeah, if you're one of the people out there, go ahead and spam the chat with the emojis if you're a channel member. And Jessica G for $2. Hey team, Spoop Dick and FDFE. I guess I'm Team Spoop Dick now. She stopped loving me again. Bella Charge for $2 New Zealand. It says you're dumb too, team. What says I'm dumb? All right. We're gonna have a good show tonight. You can already tell that they're roasting me in the chat, so we're gonna have a good time tonight. Now, Rachie, if there's anything that you would like to share or anything like that, just send it to Fight the Flat Earth, okay? And he can share anything you would like in case you don't have the ability to screen share or anything like that, okay?
Okay.
Would you prefer to be on camera or not on camera?
Probably not on camera.
Okay, not a problem. I've got you off camera as it is, so we'll just leave it at that. All right, so as with always, I always turn it over to the guest to allow you to get your word out first, so, or at least give you the opportunity to give your word first. If you'd rather me and Fight talk about anything, we can, but of course we just go with the consensus. So it's really, everybody's here to see what evidence you have. So would you like to go ahead and take over?
Sorry, were you talking to me then, team?
No, I was talking to Rachie, and I'm not.
Oh,
My
sorry,
email
cutting out
said
for
videos to
everybody.
FGFA, but it cut off.
Yeah, okay. It kind of cut in when with what you said just now. What did you just say?
I said I went to send some links to FTFA via email, but it cut off when I went to my email.
Oh, okay. FTFE, she's gonna send you some videos
Okay.
or links to show. So if you'll just get those links.
I
from her.
can't send him any because it cuts off.
Oh, okay. If you need to step away for a second to send him a link, your call will be open, so you can step out of the call, send him a link, and then come right back in the call if you need to. Or if you would like to give us, we'll give you a few minutes to go ahead and get the links out to everybody or to Fight the Flat Earth. Illuminous Poo for $5.
You can put me up on screen if you want, team.
Okay, I'll do that. Give me 1 second. Illuminous
Just want to
Poo.
say hello to Crumb TV in the chat. There's another flat earther that I will be debating shortly.
Illuminous Poo for $5. Nemesis Wanted. I'm in the hiking and kayaking by day, vengeance and justice by night, crime lord or deformed megalomaniac preferred. Yeah, I'll be your crime lord. We won't get much crime done, but I'll be your crime lord. All right, we're going to give her a second to send FTFE his, send FTFE those links, and then we'll get started with the debate.
Yeah, put me up on screen because Crumb TV thinks I'm afraid to show my face.
Oh yeah, you're on screen. And I should have everything set up by my next live stream to be back on camera, like all the lighting and stuff like that. I went and got a stream deck today to make it easier to do transitions while we're doing live shows. And it's supposed to help, I guess, with recording as well, using the stream deck. So I went ahead and invested that money into that. Definitely wasn't cheap.
Have you got a limiter on me? Because it keeps cutting out.
No.
There's one on my side.
Turn down your gain if it is. All right, let's look over here at chat real quick and see what they're all talking about while we wait for her to come back. Oh, Johan Roderick, yes, sir. My man became a member. Love it, bro. Thank you so much. Let me, yeah, I've got to get this right. Let me get over here to another page so I can send emojis out. I can't not fucking thank people with fucking proper emojis. What you got coming up, Fight?
Debate tomorrow. And then the next day, I'll be releasing my episode 47 of Flirfs Are Idiots. That's a different one because I'll be covering a Karen or a Ken, whatever you want to call him.
Yeah. So okay.
I'm quite proud of the thumbnail for it.
Have you already recorded it yet?
Not quite.
Not okay. Well, I mean, you have some of it.
The script, and I was going to record it tomorrow. Why?
All right. So, no. I'm saying we need to come to a consensus. So, see, I've done all the scavenging across the internet that anybody would need to do, and the overwhelming consensus is that a male Karen is a Kevin, not a Chad. That a Chad is more like a Biff. You know what I'm saying? Like a meathead. You know what I mean? Like a very alpha male, testosterone-driven person. So, what do you think, chat? I was about to say, what do you think, Chads? No, what do you think, chat? Are we going with male Karens being Chads, or are we going to go with the internet consensus and call them Kevins? I'll make a video moving forward. And while you guys vote, here's what I also want to tell you guys something. I have, excuse me. I've got one thing a little wrong, and I've noticed, or I've said ahead of time that I knew I was probably wrong because I wasn't like a constitutional, someone who studies the Constitution a lot. But being that I've covered a few of the First Amendment auditors, and now I'm covering these Karens that are anti-maskers, I've had to look into the law a lot more. And what I've been quoting as the law that gives the states their rights to make laws, I've been saying it's the 14th Amendment. Now, to my credit, I've said I'm not 100% sure. I might be wrong about this. Look it up. But it's not the 14th Amendment. It's the 10th Amendment. The 10th Amendment is what gives the states the rights to create laws. But I'm not going to break anything down just yet because I don't want to get into my next video. But I have a video that I've put a lot of research into that's kind of like the legality behind masks, specifically in the state of California. So I got a politician or someone who's in the political arena to take down and go after for spreading false lies. And she's on my marked list. We'll put it like that. She's on my marked list. I'll be paying attention to her because everything she puts out.
I've got the links from Rachie.
Okay, and I think she's logged back in as well. So let me go ahead and read these super chats real quick, and then we'll get started. We have Jessica G for $2. I still love you, alien kid. Yes, I know you do, Jessica. You're my favorite troll, by the way. Out of everybody that trolls me in the world, I appreciate you trolling me the most. Ilya Moon for $5. Don't forget you're on my show Saturday, team. You said to remind you. Also, love y'all. Thank you very much, Ilya. I will be there 100%, and you're still gonna need to remind me though on Friday. Rangerman 9404 for $5. I saw the discussion about face covering last night. FTFE. I didn't know you were such an avid mask debater. And mass debater is in
I
quote.
wouldn't say I'm a mass debater, but I don't like team killers, and it's not like there's science to argue about it. It's so simple. You wear a mask, or you don't get to be part of society right now. And it's not about you. All these people are like, you can't tell me what I'm supposed to do. No, we don't give a fuck about you. It's about everybody else. And it's simple. If you refuse to wear a mask in public places, you are a team-killing fucktard.
Ding. All right, we have Carrie Oliver for 3333. The dumpster fires have been strong lately. Don't get me wrong, because we love them, but I think we're all ready for a nice, calm discussion tonight. Something new, I hope. We could try that approach. In fact, we have PhD Tony that's all.
If you like.
I mean, yeah, we can. If it gets, we could just naturally. I don't think we ever shoot for a dumpster fire. I just think that's what happens. So we'll see what we can't do tonight. PhD Tony for $5 Aussie dollars. I have to go pour liquid helium into a superconducting gravimeter. Stupid non-existent force. You guys have fun. Oh shit, fucking PhD Tony. You have fun doing some science. I wish I was where you're at right now. Bella Charge for $5 New Zealand dollars. Team is a beta male. I would call myself a Charlie Cuck more than a beta male. That seems to be what goes around in the through the flat Earth community when it comes to me. Professor Pineapple for 20 Aussie dollars. Aussie, Aussie, Aussie!
Oi, oi, oi.
Love you, all of you, including my Aussies. Team, tell your sidekick, that'd be you, FTFE. Tidy shirt that team, tell your sidekick tidy shirt that pineapples rule. Yes, they do. I love pineapples. And I know what he means. He means on pizza, but we haven't got to that demonstration yet. JL Truth for $4.99. Yeah. We're all still recovering from the nuclear fallout from last time. Yeah. Well, get ready. It should be a good time. Rachie, are you there?
Yeah, I'm here.
All right, good deal. I apologize for the super chat thing right now, but we're going to turn it over to you and allow you to present anything you'd like to present. Now, since Fight the Flat Earth is full screen, all you need to do is tell him which link you need him to present. He'll present that link and we'll give you as much time as you need. Now, I'd prefer that we go point by point. I know you may have several points to bring up, but I would prefer if we do 1 point at a time. I will definitely give you time to cover as much time as you need to cover any point you need, and as well as much time as you need to explain anything that me and Fight the Flat Earth may bring up. Will that be okay with you?
Yeah, that's fine.
All right. Well, I'm going to turn it over to you, Rachie. You have the floor.
Okay, well, basically, I think that gravity is just density. I know you've heard this before, but I've done some maths and some equations, and they've turned out just fine without using gravity or acceleration. And I do believe that these links that I've sent, Fight the Flat Earth, do prove that it is just density in the medium of the density surrounding it. If he clicks on the first link, it's a helium balloon going left in the car. Obviously, because he drives forward, the helium balloon goes to the opposite direction to where the density of the air goes. So he'll actually explain that in the video as well.
Now we have the plumb bob right next to the balloon, so if I go forward, they should spread apart, right? Check it out. Is it working? Yeah. All right. So what I'm going to do is I'm going to tell everybody on Smarter Every Day that if they...
Is that enough, or do we need to show more of it?
No, that's fine. So basically, as you can see, the helium balloon goes the opposite way to the most dense air. So he says that the children in the back have more dense air, have more air. So that means the more air is to the back, and the balloon goes the opposite direction. Just like, on Earth, the balloon will go up the opposite way to the density of the air. So that's the first one. That's kind of proving my point. What I'm trying to say.
Okay, can I ask a question?
Sure.
Okay, so when you're talking about acceleration and you're talking about forces that are felt within the reference frame, this is one of the ways that we can tell that a reference frame is inertial versus non-inertial. It's similar to like when he takes off, the balloon from the perspective of the camera looks like it moves forward. Now we know that there's no actual force pushing the balloon forward. So we create it's well, there is a force, it's the buoyant force, but we know that the gravitational force, or the force of acceleration, is not it's a fictitious force. It's not present in the frame of reference. You know, like you don't see it, you know what I mean? It's like, you know, it's not something pushing the actual balloon, a physical force pushing the balloon, you know what I mean? So what ends up happening is as the car goes forward, the fictitious force is in the opposite direction of acceleration. This is why there's an alignment of the heavier gases down towards the back of the car, is because of the acceleration. Now, if you'll notice the balloon does not go 90 degrees. It does not tilt 90 degrees and point forward in the direction of acceleration. It tilts about 45 degrees and points a little bit forward and still a little bit up, so, denoting that there's an acceleration that's not directly back from the car, nor is it directly down. It's actually a combination, a mathematical combination of both accelerations. And that's why the balloon only goes to a certain angle. And I believe they do explain this in the video towards the end.
So okay, but I might argue that point, saying that the most... Sorry, go on, Flat Earth. Well, I was going to say...
Rachie, one second. Just so you know, there's a delay between me and Fight. So if y'all both start talking, it's because he hears a pause. But if you start talking when he's talking, then that's just because he's delayed to us. So you just keep talking, and he'll let you finish your point, and then he'll come in after that. Go ahead, Rachie.
Okay, I was going to say that because most of the most air is at the back of the car, that means that's the most dense bit of the air around the balloon. And then obviously it still has some at the bottom, so that would possibly be a reason that it doesn't actually go 90 degrees, because the air is still at the bottom, so it still wants to go up.
Okay, so in this situation, what you would need to do is you would need to go to the back of the car and ensure that the density of the back of the car is the same at the bottom as it is at the top of the car. Because without that density, if there's a density gradient, then the gradient needs to be explained. Now, my prediction would be that there will still be a density gradient in the back of the car. It'll just be different under acceleration and than when the car is not accelerating, when it's traveling at in an inertial path.
So what's actually happening? Okay, when the balloon is, when he's driving forward and the balloon moves forward, there's a reason for that happening. Okay, and it's because there's a force being applied. Now, because he's accelerating forward, what it does at this point, right, when the balloon is going forward, the reason it's going forward is because as he accelerates forward, the heavier air gets pushed to the back of the car, right? And that makes it more dense at the back of the car, which means that there is a force applied in the opposite direction for the thing that's lighter than the air, which is the balloon. But it has to have a force in the opposite direction, right? And that's the point of buoyancy. Now, buoyancy, the equation for buoyancy is rho vg, right? And that g stands for the acceleration due to gravity. Now, in that car, the equivalent of the acceleration due to gravity is the fact that the air is being forced to the back of the car as he accelerates. My point is that there has to be a force. There has to be something to create that buoyant force for something to move. Density of the medium and the thing alone isn't going to affect anything. It's all to do with the fact that there has to be a vector applied, a direction applied to something. And that's only applied if there is a force. Gravity is what causes things to go up because there is more dense air being pulled down around a helium balloon. And it's the same in the car. The more dense air is being pushed to the back.
Okay, so you're saying that it's because the acceleration, basically?
Yeah, there has to be something to give it a direction, right? And density itself can't give anything a direction. You have to have a vector, and the thing that gives buoyancy that vector is the acceleration towards the center of the Earth. which then creates a buoyant force in the opposite direction to the local gravitational vector.
So what you're saying is that force gives something a direction.
Yes.
Well,
Then
by
what
definition,
brings
force,
the sunlight to the Earth?
the
Well, that's a
electromagnetic
completely
force.
different thing. That's nothing to do with
But
buoyancy or
it does
anything.
move. The light does move. So if light moves, is that not a force? Like, because it's moving.
Well, there's energy being applied. Energy is, being created in the nuclear fusion center of the sun. And
So, okay.
the
So would
result
that
of
be the
that is
force?
an electromagnetic signal.
Well, okay. So when a photon is created, it becomes self-propagating, because of the fact that if you have a magnet and you move a magnet, it creates an electrical field, and a moving electrical field creates a magnetic field. So you get this, once a photon is created, unless it's absorbed by something else, it will be a self-propagating wave that will continue on forever.
Okay. Well, what force causes heat to rise? Because that has a direction. It has a direction up. So what force causes it to go
That'd
up?
be the buoyant force. So as a pocket of gas, let's say, was to start it heating up, it would expand. Now, as it expands, it becomes less dense. So the buoyant force actually acts on that, would reduce
Team up back 1 sec.
yeah, that would reduce the density of the gas, and the buoyant force would take over, just like it does with a balloon. It would just push the gas up.
Okay. What
But
about
only
hot and cold mixing? Hot and cold water when they mix. What force is that causing them to mix?
I'm not sure what you mean by that.
Well, if say you have a bath of cold water and then you start to add hot water in, they will start to, like, the molecules will start to mix and go in all different directions. So what causes it to mix and
Well,
not
that's
stay
just
hot one side and
because
cold another side or something?
that's a conservation of momentum. So when you have a hot particle that hits a cold particle, some of its energy is transferred into the cold particle. So the cold particle heats up a bit, and the hot particle cools down a bit, because the energy is transferred from one particle to the next.
Okay. I don't know whether you believe in poltergeist activity, but what about that force?
I don't. So I mean, you'd have to give me like a demonstrable situation that I could test for myself.
Well, that's the problem, ain't it? You don't know when poltergeist activity is going to happen.
But see, that's the difference between natural and supernatural observation as well. See, natural observation, sometimes, like, it doesn't have to be something that we can manipulate, but it's nice when we can manipulate it, so we can, control it as much as possible, provide as many control variables to ensure that what we're seeing or experiencing isn't just like either a fragment of our imagination, or, maybe a missed observation or a misobservation where you think you see something that you don't actually see. I mean, people make mistakes all the time, and people are heavily influenced by, emotions and mental states, as well as, brain chemistry. So unless it was something that was demonstratable, or, something that you and I could go and do together and say, this is what we expect to happen, and then we go and we confirm that's what happens, then it's not something that I typically find myself believing in.
Fair enough.
Tim, could
Okay,
you do me
well,
a
we
favour,
might as well
send me a
skip the
fresh
second
link?
link.
I'm having it cut out a lot. So could you just send me a fresh link and I'll join on that?
Yeah, give me 1 second. I'll send you a new one. All right, 1 second, Rachel. Let me get him a new link. He seems to be having a little trouble with this connecting. All right. And then when he comes back on, we'll let you get to your next point. Or do you understand what I was saying? That if gravity wasn't there, that balloon should not stop at an angle. It should go all the way forward when he accelerates. I mean, do you understand what I mean by that?
Well, no, because gravity pulls things down, not diagonal or at an angle.
Right.
So
Okay, that's a good point. So, let's say that you were that that guy was constantly accelerating, okay, at 9.8 meters per second straight, all right? So we have 9.8 meters per second straight, and we have 9.8. Oh, let me get Fight. Hold on, let me do something real quick to make sure that Fight can get in here. He should be able to join now. Okay, so let's say you have 9.8 meters straight, which creates the fictitious force of 9.8 meters per second squared going backwards, and then you have 9.8 meters per second squared going down. So what you would do is on an object, let's say you were trying to measure the weight. Pull back up her video, Fight, if you can. The one where he had
on screen.
Put it. Bring him up to the part at the very beginning though, where he had the weight hanging down. Okay, so if he was to on that weight right there, stop it right there. Now, of course, he's not constantly accelerating here. You know, he's getting it going and it swings back. But with a car, it's really hard. So we have to do this as like kind of like a thought experiment. Okay. So let's say we were constantly accelerating at 9.8 meters per second squared forward, and we also just assumed at this point, that there's a 9.8 meters per second squared downward force. What would we be able to say, at what angle will that wire hang when we're under acceleration?
Well, if you believe in what they tell you, it'd be just down, straight down, nothing to be acting on it at all.
No. There would be one force
Because they
acting
cancel
down.
each other out. Yeah, but when they say about the International Space Station, they say because it's going so fast, it
It's a
cancels
little
out
bit
the
different,
effects
though.
of gravity.
Yeah. So that's a little bit different because
Wait. It doesn't cancel out the effects of gravity because it's going so fast. The thing about the ISS is that it's in free fall towards the Earth. It's falling towards the Earth. So that's why they are weightless, because they are falling. But they've got a fast enough tangential velocity that they miss the Earth. So that's why they're weightless. They still have gravity acting on them. It's about 88% of the gravity that we experience here on the surface. But because they are falling towards the Earth, like in the Vomit Comet, you know, the airplane that does the parabolic flights, when it's diving down towards the Earth, the people inside are weightless. That's why the ISS, they're floating.
That's not actually true. They start going weightless as they go up. There's actually a video on that, but I'm not sure. I haven't actually got the link to it. Where there's some geezer and he's saying that when you go up,
weightless as they go up.
yeah, he's got the nose of the plane pointing up, and that's when it starts going weightless. He's the one that does all these different experiments. He goes in like the anti-gravity where it's going like centrifugal force and it's spinning around.
Not
He's
how
that
physics
person.
works.
That's what he said in the video.
okay, so
I'd like to see that video.
when you have an object in
I'll
a
send you a
reference,
link to it.
in this video that we're looking on screen, if you need us to pause so you can send the link, let us know and we'll take a break. But in the video that we're talking about on the screen, from the camera's perspective, the opposite door, all the chairs, all the kids, the windows, and everything remains in place except for the swinging string. Okay, so that's how we know that this is an accelerated reference frame. This is an accelerating or non-inertial reference frame. So all objects within that reference frame will appear to have an acceleration that is downward, as you can tell from the string hanging down, and then also backwards, and this is because of the car accelerating forward. Since we have both of those accelerations, they don't cancel each other out, or gravity doesn't just take over. They actually, the total amount of acceleration that's acting on that object is a sum of all the accelerations. So it would hang at a 45-degree angle. It would be being pulled down directly down as much as it's being pulled directly back. So that's why it kind of hangs and swings a little bit, is because there's two different forces acting upon it. One, gravity pulling it down, and the other, the accelerating force pulling it backwards. Now, it's the same concept on the
I
ISS.
disagree. I say it's density pulling it down and the acceleration pulling it backwards.
Density can't pull anything down because density isn't a force.
Yeah, I mean that's
I disagree.
how do you explain density to be a force? You said you have some math, is that correct?
Well, somebody gave me a thought experiment, and it was basically a cube with another cube in a smaller cube inside by 40 by 40 by 40 millimeters one side polycarbonate with the other side glass, the other side copper, lead, polycarbonate, and another one. And he was basically asking me, would it sink or would it float? I did some maths and that without the gravity or acceleration, and I was able to tell him that it would float, so that it wouldn't sink to the bottom.
Because you determined what, that its density was greater than, or was not greater than water's?
All I basically did was I figured out how big the sides would be, the volume of the sides, and then I times each density by the volume of the sides. I then added all those together, as well as the air, times the air by the volume inside. I added all those together to get the mass of the box. And then I, obviously, because it was in mineral water as well, the big box was filled up halfway with mineral water, mineral oil, sorry. And I was able to tell him whether it would float or not, and by using maths to see how much would displace out of the mineral oil. But I didn't use any gravity or any acceleration or anything.
Okay, yeah, so basically you did what a shipbuilder does. He assumes gravity, and then he determines the density of the ship versus the density of the water, and then he determines how much it's going to sink down, and that's basically how ships are built, to ensure that they float. And that's exactly what you did,
There
right?
is no gravity in my equation, whereas buoyancy does have a gravity in this equation.
No, buoyancy does have gravity
hold on.
in the equation.
How did you explain the force that's going to hold up the object you put into the to the liquid solution?
It's just density. So
okay.
basically,
Hold on.
It's not just density. That's not actually technically correct. It's not just density. You have to figure out the mass of the small cube with all its different materials densities. You have to figure out how much it would actually be, the mass would be, and then you figure out how much the mass of the mineral oil would be, and then you can determine whether it would float or not.
Okay, so let's do this thought experiment together, and I'm gonna walk through with it, because I'd like to break this down, because there's a great point to be made here. Okay, so let's say we have we have a bowl of your mineral solution, okay, and the bowl is deep enough so that we can set the object in, and the object will either float, semi-submerge, or sink all the way to the bottom, and I'll allow you to make a prediction, okay? So if I take this object and I hold it, that we'll say 2 inches above the mineral water, and I let go, where will the object go, and why?
What is the object? Like, what density?
The object you were talking about, the cube you were talking about.
If you just let it go in the middle of the air to fall towards the mineral.
Yes. Where will it go and why?
It'd fall down into the mineral oil, but not to the bottom.
Okay.
But it depends on, like, obviously, with the density of air cube, if it's still the same cube, then yeah, it'd float, but it'd be submerged a little bit.
Okay, so
I'm
why
not exactly
would it...
sure how much, because I'm still working on the equation for how much the water line would be, so to speak.
Okay, so why would it fall, though? Why would it begin to fall when you let go of it?
Because it's more dense than the air that's all around it.
Okay, it's more dense than the air that's all around it. So, but why would it go down instead of up?
Because things that are more dense than the air, so things that are more dense than the things that's surrounding it will fall down. If it's less dense, it will go up.
Why?
Because it's more dense. More dense down, less dense up.
Okay,
there's there's a pressure gradient on Earth. There's a density gradient.
Okay, right. Okay. For instance, let's take a vacuum. Okay, you put a helium balloon in a vacuum chamber, and it's going to go towards the ground. All right, it's going to fall. Yeah. Now, there's no medium in it, so technically the medium all around that helium balloon is exactly the same. So how does that helium balloon know to go towards the ground? What's making it go towards the ground?
There is no density of the vacuum because there's nothing there. So the density of the vacuum is 0. So therefore the object is more dense because the density of the vacuum is 0.
Yeah, so I get that. But how does the balloon know when the density all around the balloon is exactly the same? Why doesn't it go side to side or go up? What is telling it to go down rather than any other direction?
Well, that's what I'm trying to say with that car and that, like, it was going left and right depending where the most air was.
Okay, so
Yeah,
let me
but that's the point.
rephrase.
In the vacuum chamber, there is no air, right? There's no air
Exactly.
there. So how does the
So it
balloon
has
know
no
which way to
density
go? Exactly.
because it
At
knows
every
it's more
point
dense.
around that balloon, it is exactly the same density. So how does the balloon know to go down rather than up or to the side?
Because there's no density around it, so therefore it's the most dense. It's most dense, so it goes down.
Yeah, we get that, but why? Why? My point here, Rachie, that you're missing is that all around that balloon, the density is exactly the same. Above it, below it, left and right. So why does the balloon go down instead of any other direction? Why? How does it know to go down?
Because it's more dense. If it was like more dense, if it was, I don't know, for instance,
That
say
doesn't
we had
answer the question.
But hold
I'm
on, Rachie.
trying to answer it. Hold
Rachie.
on a second. If we had, for instance, if we replaced all our air with something a lot more dense, and we had an object that was less dense, then it would float
Why?
because it's density.
Okay,
That's
so
right. Just saying its density doesn't answer anything, Rachie. Listen to what I'm saying to you. In the vacuum chamber, that helium balloon has no way to know which way is up or down. Okay? There is no medium around it. At every point around that balloon, there is exactly the same density. So why does the balloon go down instead of up? You can't just say density. How does density give anything the direction? It doesn't know to go down. Density is just mass per volume, mass over volume. That's it. So why would the balloon go towards the ground rather than any other direction?
Because if it's more dense, it goes down. I don't know why it does, but because it's more dense, it goes down.
No, that we do. We know why, because of gravity.
yeah.
You're going
So
to say gravity, I know, yeah.
so okay, are you saying then that it's attracted to more dense objects, like whether it be just a band of air or the ground itself? All things are attracted to more dense objects.
No, I wouldn't say that. No.
Well,
I'd
then
say
why does it go down instead of up?
because there is zero density around it, so therefore that is less dense. And if it's less dense around it, it will go down because it's more dense.
Okay, so you're saying the
but
relative
as you
density
just
to
said, you
the
don't know
environment,
why.
right? You're saying the relative density to the environment, correct? So you're saying because there's no density in the environment, and no matter what density an object has, because there's no density around it, it will always go down, correct?
Correct.
Okay, that's what gravity predicts. So while
And
you
that's
don't
what
accept,
density predicts.
no, it doesn't. Density doesn't
No,
have
it doesn't.
a direction, because, like Fight says, look, if I take a ball on the inside of a box, and we're going to say that the box is completely closed, so that the ball on the inside has no way of knowing or we'll say we put you inside of a box. It has plenty of oxygen. You'll survive for days. We only need to do this for 30 seconds, okay? Now, theoretically, if you're made of helium and you're floating around in that box, how would you know which way down was? So you say, well, I just know I'm go that way, so that way is down. Well, now let's say I turn the box upside down. Do you now go up because the direction of down is now pointing up, or do you start falling what used to be up, which is now down?
Well, the thing is with gravity, they tell you that it has like no direction pretty much, like because it's like a globe or whatever, like, you know, it's like
No, it has a
pulling in
direction.
every direction.
No,
Yeah,
it
it's
has a
like pulling in
direction.
every direction all around the globe. So on this side of the globe, it's pulling in this side, and the top of the globe, it's pulling down. At the bottom of the globe, it's pulling up. Like, so technically, it's always down to everybody, but it's not really always down. But like,
Towards the center of mass is what you're
Yeah,
trying to
towards
say.
the center.
yeah, but because like obviously you're saying it's like when you tilt it, why don't it go the opposite direction? Well, because it's more dense, and on Earth, down is down towards just towards the surface of the Earth, and up is
But
away
why?
from the surface
But
of the
why?
Earth. So because it's like how you have a pressure gradient, you also have a density gradient. So
Not
obviously
in
the
a vacuum.
surface is like,
Not in a vacuum, we don't, though.
but it's still more dense than the nothingness around it, so it falls.
Well, yeah, but you're still not giving us a reason as to why it falls. Like, okay, so you agree that Newton's laws of motion are pretty sound, right? I mean, Newton's laws of motion don't involve gravity whatsoever. They just say that an object at rest will stay at rest unless it's acted upon by an unbalanced force. So basically, I set a bowling ball on the ground. The ball isn't going to just start moving on its own. Something will actually have to go and give it a force to make it start moving, correct?
Agreed, other than poltergeist activity, but yes, agreed
okay.
other than that, yeah.
But even if the ball moved like that due to poltergeist activity, there would still be a poltergeist enacting a force onto the ball to move it, correct? I mean, it wouldn't just move on its own without the help of something supernatural, would it?
Okay, I can agree with that.
Okay, so if I hold a ball out and extend my arm and let go of it, okay, I have not put a force on it whatsoever. I've just let go of it. As long as no force is applied to it, no acceleration should happen, and the ball should not move. It should sit there in midair, according to Newton's laws of motion. But they don't. Every time we do that, the ball falls to the ground. In a vacuum, in atmosphere, it doesn't matter. Why is that?
I'd say when it's on the ground, it doesn't have a force. Like, when it's on the ground, there's no force acting on it, and then when you pick it up, there is a force acting on it because you've picked it up. And then when you let go, it's more dense than the air, so it falls.
Go ahead.
When you're on the ground, there is a force on you, and that's what you feel. That's called weight. When you step on scales, you are feeling that force. The scales are registering that force. So there is still a force acting on you when you are just sitting on your desk. Now, I've got two questions for you, Rachie. Right. So if it's all to do with density and nothing else, why do icebergs sit mostly under the water and partly above?
Because I'm not exactly sure of the density of ice, but I'm pretty sure it's less dense than water, so it wants to go up, and it's more dense than air, so it wants to go down. So if you like, there's a force pushing it up and a force pushing it down, but that's just because it's less dense than the water and more dense than the air.
If it's less dense than water, it's less dense than water, so why is some of it, why is the majority of it underwater?
The same way the hull of a boat goes underwater. It depends on the surface area and the volume and how much it displaces in the water. The same as how a boat floats. It has to displace a certain amount of water.
You said it's all just to do with density and
it's to do with density, why things fall, why things float are different.
See, not really. You have to be able to explain both things, right? And with gravity,
I can explain both things, but you have to remember density is mass.
Density is what?
No, density.
Density is mass. Density is times volume, which is mass. So if you times the density by the volume, you get the mass. So basically, all it is how much density, how close the particles are in a given volume. So, like, you can have them so close together, that means you got more density, and then times it by the volume, it gives you the mass. So all it's telling you is like how much material and how much matter, but that is the weight. You can't expect something to have matter without having weight.
No. Weight is a result of a downward force acting on mass. Mass and weight are different things, right? A mass, say 100 kilogram mass, will actually weigh slightly differently the equator and the poles because of a difference in gravity and centrifugal acceleration. Density couldn't explain that, right? Now, okay, but
it can explain that because you can have a pressure difference and a temperature difference, and if you have a pressure difference and temperature difference, both of those things.
There's nothing to do with that. It's nothing to do with a pressure and temperature difference that will change the actual weight of things. It's all to do with a difference in acceleration.
Now,
it's
I do want
to do with pressure and weight. We disproved that. But one second, I wanted to ask her my other question with this thing here first, right? So using your density stuff, right? Can you predict what direction that block of wood will go when he lets it go? Is it going to fall towards
no, I can't predict where it's going to go because I don't know where the density is. So, like, for instance, if there's any wind, it could go in a different direction.
it's 100% clear that the more dense thing is behind it, right? Underneath it. It's a lot more dense. So according to what you've been telling us, it should go through the less dense medium of the air towards that more dense thing underneath it, right? That's what your equations and everything would predict.
Well,
Yeah.
one, I can't tell whether that is a wall or a floor. It could be holding that up against the background of a wall
matter.
or a floor.
Yeah,
That's not the
yeah,
point.
but why would the direction of what we say is the pull of gravity mean anything to somebody who says gravity is non-existent?
Well, the thing is, you're going to
It's
say
just
it's
all to do with
gravity, but since
density.
when has gravity ever pulled anything diagonal? Because I've seen that video and it pulls it down like diagonally towards the bottom right. Gravity does not pull things
And then-
diagonally.
yeah.
If Isaac Newton had seen an apple falling diagonally, he would have come
using
up with a totally
gravity's
different theory.
equations and knowing the direction, but using the predictive powers of gravity and knowing the direction he has his camera, we can predict which way that would go. Your predictions say it will go through the less dense medium towards the more dense thing, which means it would
Yes.
fall backwards towards that wall. That is what you predict. There is no way to tell that when he lets it go like he does here, it's going to go down towards the bottom right. The only way you can do that is with a force being applied, an acceleration.
And gravity
Acceleration
doesn't
is
pull
gravity.
things diagonally.
You cannot explain that.
Neither
No,
can
but that's
gravity.
just,
Gravity
predict
pulls
which way
things
it would
down.
But it's not pulling it diagonally. That's just the orientation of the camera. See, with your explanation, the orientation of the camera should mean nothing. There should be one surface that's more dense than another, and an object should always go towards the more dense object.
But
you
you
know.
have to take into account any wind, or if there was more dense air on one side
Okay,
than
but-
the other, then it's going to go in another direction, like the helium balloon I was trying to say in the car light.
More dense air than no.
On
It's
one
pretty
side
much
than
gonna
the
be
other.
same around there. The
But,
thing is,
It depends
Rachie,
on wind.
density alone has no predictive powers. You cannot tell which way things are going to go. And my vacuum chamber question to you completely destroys your argument 100%, because even you said,
But you can't.
well, I don't
You
know
say you
why it
can't
would go
tell
in
which way
particular.
it's going to
No,
go,
hold on,
but I
hold
can
on,
tell
hold
whether
on,
the cube is going to float.
Hold on, wait. You even admitted, Rachie, that you cannot say why the helium balloon would drop down in a vacuum chamber. There is no reason with the things that you were saying for that to happen. However, there is a reason that explains that and everything else we talk about, and that's gravity. And the fact that you cannot give an explanation for why that destroys your argument. Absolutely 100%, it's dead. There is no coming
But I
back from
told
that.
you why it
It's
goes
done.
down, because it's denser at the bottom than it is at the top. So it's like you have a
Doesn't
pressure
know that,
gradient.
though.
You
The
also have
balloon,
an
no,
earth
no,
gradient.
no,
You
no,
see?
Rachie, the balloon doesn't know that.
All right.
Rachie, no, bollocks. No,
I
I'm
wanna
not
say
having you go
something.
back to that. The balloon does not know. There
Okay,
is no way to tell for the balloon which
It doesn't
way
need
is up
to know.
and
It's
down.
the density that matters.
Rachie, I want to ask you a
Density
question.
doesn't know anything.
Put that picture back up, Fight, please. All right, so given this situation right here, if that wall was coated with, we'll just say like something real dense, lead. Okay, we'll say it's lead because lead's much more dense than the surface of the Earth. Would that object then go towards the wall, or would it go to the less dense Earth?
Well, it's not surrounded by it, so it wouldn't matter. It's not immersed in it, if you like.
What does that have to do with anything? The Earth is obviously
It has to be
underneath.
immersed in something.
Okay, so let's say it's immersed in the atmosphere. Let's say we just replace that plaster wall with a lead wall. Okay, something much more dense than the surface of the Earth. If I let go of this object, will it go to the lead wall? Very thin lead wall, okay? We're not talking about huge. We're talking about very thin lead wall, but more dense than the Earth. Or will it still fall to the Earth?
It'll still fall to the earth because the air around
Exactly.
it is less dense, so it falls
It has
down.
nothing to do with the air.
It doesn't fall sideways or sideways because that only happens if the air was more dense on one side. But if the air's the same on one side, then
So if I have a cylinder, if I have a cylinder with a marble in the middle of it, okay, and let's say I take the cylinder and I suspend the marble from the top of the cylinder down. All right, so we've got gas in there, and according to you, it's being pulled down because there's the more dense air will be at the bottom and the less dense air will be at the top. Well, let's say I flip it real quick, okay? I flip it real quick. Now, the moment I flip it, the top of the cylinder is still denser than the bottom, but the marble on the inside will immediately begin going towards the earth, towards the bottom of the container, even when the gas has not had a chance to switch its densities and align itself so that the more dense is at the bottom.
I agree, but it doesn't really matter about that because like it's still more dense than all of it.
It's more dense than what?
Do you know what I mean? Like it's more dense than all the air. It doesn't matter
then,
like if it's
yeah,
a bit
But
less dense on the
density
top or a
can't
bit more
tell it
dense
to
on the
go a
bottom.
direct.
But you literally
But
just
density can't
said,
tell it to go a direction.
okay, so let me re-clarify my thing, okay? Let's say you have a marble in there where it can move, but no air can go on either side, okay? But the marble itself can move in the cylinder, but air cannot go from one side of the marble to the other. All right, so when you have it in one orientation, the marble is being pulled down, it compresses the gas at the bottom, and that gas is more dense than the gas at the top. So if I turn this over, that marble should never move because the gas at the top is more dense than the gas at the bottom. It should never move.
No, because
but
the marble
because-
is more dense.
But that doesn't matter. You already said that things are
I'm
pulled
saying
because
if
of
it's
the
more
density in the
dense,
air. But you're saying
yeah,
things
if
are
it's
being pulled
more
by the
dense than the air around it, then it will fall down. So it's more dense than all the air around it, so it will always fall down.
Why?
That's not what you said earlier. You said
Whereas
earlier it falls down.
because I was
Wait,
on
hold
about the helium balloon then going left and right because
Okay.
the helium balloon is lighter than air. It's like less
So-
dense than air.
Why does it have a preferential direction of always being down?
I mean, you could call it a law if you want. Like, you know, the first
Yeah,
law is if
I
it's
mean,
more dense,
no,
it falls down.
No, we do have a law. It's called the law of universal gravitation.
Okay, well, you would say that the force is because he times it by what, 9.8 or something like that for gravity.
No, the law of gravitation.
He gets
has
the
nothing to
mass
do
and
with
he times it
9.8.
by g and it gives you the weight.
Okay, yes, the acceleration is big G times the mass that you're being attracted to over the distance from the gravitational center squared.
And if you times the mass by the gravitation, you would get the weight in newtons.
Well, no, if you times the mass times the acceleration, yes, you'd get the weight in newtons. Not times the gravitational constant, but by times the acceleration, gravitational acceleration.
And those newtons, when you times it by that g, would be the force.
No, that's something that's derived from Newton's equation F equals ma.
But again,
So if you have a 1
if
if you have a 1 kilogram object that's under 10 newtons or 10 meters per second squared acceleration, then it's going to have a force of 10 newtons underneath it. That's what weight is. Weight is the force. You start at the equator.
That's what I'm trying to say. So weight is the force.
Yes, acceleration times mass. Unless you have a way of.
So when he times mass by like gravity, he ended up getting the force, and the weight is the force.
Yes, weight is a force. Yes.
Okay, so but all he did was times it by the rate things fall, but things don't always fall at those rates. Like obviously, there's other things like resistance and things which slow things down. So
Right,
things
but
don't
we
always
can
fall at that
fully
rate. But yeah, he
explain that.
timed things by those weights.
But yeah, when you
he
remove
times
under
it by
controlled,
the rate
okay,
that things
so
fall.
under controlled circumstances, like a controlled experiment, you can eliminate those factors, like by creating a vacuum and dropping things in a vacuum and testing that theory out or that law out in a vacuum, which they've done several times. And you can do this at home. You don't have to have a huge vacuum. You can buy like a little vacuum kit for like $100 online. You can create a vacuum in the inside and watch your little helium balloon fall to the ground.
But don't you find it weird that he times it by the rate that things fall and called it a force?
No, they explain that when an object accelerates, when an object with mass accelerates, it generates a force.
But all he did was times it by the rate that things fall, which all things don't actually fall at that rate.
Hold
and
on.
called
It
it a
doesn't
force.
generate a force. It has a force to it. You can define the force that it has with the mass times acceleration.
But why does he always times it by that number? Things don't always fall at that rate.
Because they do under a controlled environment. like when you're in a vacuum
But not in
chamber.
everyday life. Like if you've
It
dropped
doesn't
something in
matter.
liquid or you drop
That's
something in
that's the crazy thing. He came up with this without even having to understand that they knew at the time feathers didn't fall at the same rate as bowling balls. They knew that. So what you're saying has nothing to do with his personal observations. Otherwise, he would have changed it.
But I just think it's silly that he times it by like not the rate that things fall.
So he didn't do that.
Because
But he didn't do that. He didn't do that. He took the observations of Johannes Kepler and made sense of those observations. He saw that there were certain reasons that Johannes Kepler were able to come up with these 3 laws of planetary motion, or his laws of planetary motion. So Newton followed behind that to explain that gravity was like a centripetal force. Okay, so they didn't understand what gravity was at the time. They just knew it acted on objects. They knew objects needed to have a force acted upon them, and this is the relationship they saw between orbits and bodies of mass. Now, the gravitational constant is just a way of making sense of converting the relationship into units that we can use, force units.
But when I look at like newtons and there, I think, well, it's just another form of weight because like you've got stones, pounds, kilograms, and things like that. Like you can times 1 pound by 14 and get a stone. So all he did was times it by 9 and got like newtons. So it's just another form of weight.
But he didn't do that. He didn't do that. He didn't do that. That's not how he came up with his laws of motion and the law of gravitational attraction. The idea that an apple fell from a tree onto his head is a complete story. It's something you tell children. It's not actually what happened. What happened was involved him observing Kepler's observations. See, they all build off of each other. They all learned from the last guy.
That's the problem as well, ain't it? We always like lie to people, you know, Santa's real and things like that, and an apple fell on his head and this, that, the other, which ain't even real.
Well, I think just a story. I think telling a story and understanding it as a story is completely different than telling a fabrication in an effort to confuse somebody or to convince them of something that's not true. That's completely different. Nobody's saying that the law of gravitation absolutely relies on the story that an apple fell from a tree onto Newton's head. It's something we just tell kids. It's a story that got embellished over years and years, but it has nothing to do with what actually happened. With what actually happened is that he noticed that there was a relationship between Kepler's observations and also things that would fall on Earth at the same rate. It had the force, the F equals ma had nothing to do with the law of gravitation. It was a law of motion.
Okay, but again, I've done like equations without the gravity or the acceleration, and you know, I've managed to determine whether something would float or sink. Well, you can, but they're kind of long.
You've given what you've done. You've given an arbitrary number to density and basically said, well, if it's higher or lower than that, that will determine if it goes up or down. When that doesn't work.
No, because it was a cube and one side was tin, one side was aluminium, one side was glass, one side was polycarbonate, one side was copper, one side was lead, so no.
That's irrelevant.
And all those are more dense than the mineral oil, so you would think that it would sink.
Rachie, you also make an assumption that everything with density goes down. Everything that's more dense goes down.
It's more dense than its surroundings, but it depends on whether it's a liquid, a gas, or a solid.
But you make that assumption without explaining why you're making. Yeah, exactly. Why are you making that assumption? We don't make that assumption over here. We understand the relationship between the gravitational pull and things like the buoyant force. You don't. You're just saying, oh, well, don't worry why it goes down. It just does. Well, that's not good enough for me.
I'm saying it goes down because it's more dense than its surroundings. A helium balloon will go up because it's less dense than its surroundings.
Why?
But
you keep
why?
saying
not everything goes up. So not everything goes down.
But why?
Yeah, but why? You haven't told us why this happens.
Because it's more dense.
But that doesn't explain.
No, just saying that doesn't give us any answer.
Okay,
it's more dense doesn't matter because, like I've said with the vacuum chamber, Rachie, and this destroys your entire argument again. There is no difference in density around the balloon. It is the same at all points. So why does it go down? How does the balloon know that it has to go down? in a vacuum chamber.
Rachie, let me give
I
you.
agree.
Let me
There's
give
nothing
you
around it. So basically, you've got 0 at the top, 0 at the side, 0 at the bottom. So the helium balloon is more dense than the 0 here, the 0 here, the 0 here, and the 0 here. So if it's more dense, then all of that will go down.
Why?
Why not up?
Yeah, we already
Because it's
explained.
more dense. That's how it works.
Hold on. But we already
If it was less
explained.
dense,
No, hold on. No. Just saying that's how it works doesn't give the answer. The density is the same all around, so why down and not up? Not just it does, that's the way it works. Why?
Well, I've told you because it's more dense.
That doesn't tell us anything. How does the balloon know it's more dense?
Okay, so
it's the same all around.
All right, but this is what we're trying to tell you is that
Oh
when we start from the beginning, before we talk about gravity, we start from the beginning and we say that for a mass to accelerate, for it to go from 0 miles per hour, no motion whatsoever, to any motion whatsoever, there must be a force that acts upon it, okay? So if we're in let's say we have a helium balloon at the bottom, at the surface of the earth, outside, and I have it in my hand, it's not going anywhere. I let go of it, you will agree with me that it will accelerate upwards, correct? Away from the surface of the earth.
Yeah.
Okay. What is the force that made it accelerate in that direction?
Well,
Or the
me
sum of
myself, I
forces.
wouldn't call it a force. I'd just say it was because it was less dense, so it would go.
it's a force
You
because
don't
the
get
mass.
to say where it's a force or not.
So for the mass to accelerate, a force must act upon it. Okay, that's what we're trying to tell you.
Are you disagreeing with Newton's laws?
Yeah, according to Newton's laws of motion, this has nothing to do with gravity at this point. This is simply his basic laws of motion. I'm holding a balloon out. It's not moving anywhere. I let go of it. It accelerates upwards. There was a force applied to the balloon that caused it to accelerate upwards. That force will be a sum of all forces acting upon the balloon. So I need you to explain with sum of all forces where the forces are and where they came from to explain why the balloon went in the up direction and not the down direction or right direction or left direction.
Unfortunately, I can't do that because I don't believe it was a force. If Fight the Flat Earth plays my last link, maybe you can tell me why it's gravity and not density.
We need to.
We'll get to that. We'll get to that.
What you just said. You don't believe it's a force. That is irrelevant, Rachie. Okay.
So at this point,
there is a mass. There is a mass. The mass accelerates. Therefore, there is a force. Okay. Unless you are disagreeing with F equals ma, that is something you can't deny. You can't just say I don't think it's a force when F equals ma. All right.
Yes.
I am disagreeing with that because you've got how many.
So you're disagreeing with F equals ma.
Yes,
to be
because
clear, Rachie,
you can have a mass.
That F equals ma.
This is the most basic law. The most basic law of physics.
The thing I'm trying to say is if you've got F equals ma, so the force equals mass times acceleration. So that means if you've got a mass of, 100 kilograms and a mass of 10 kilograms, one should accelerate faster than the other, but it doesn't. And that's when they end up bringing in the Earth's mass and divided by this and divided by that, divided by the radius and things like that. Because they put the two masses into the equation.
No, that's not how that works. Okay, I if you want to repeat that so I can address all of that one by one, that's not how it works. Okay, so look, let's look at the two equations.
Force equals mass times acceleration.
Yes. And
so then if you got one mass equals 10 kilograms and one mass equals 100 kilograms, and then you times it by acceleration, one should fall faster than the other.
No, that one will fall with more force.
Because the number would be bigger.
No, well, hold on. No. One would fall with more force. One would fall with 10 times more force.
Is one of the most insanely idiotic things I have ever heard.
I just wanted to get that out.
Yeah, one will fall with more force.
You times it by acceleration, so doesn't that tell you how fast it would fall?
Yeah, hold on. Give me 1 second. Just give me 1 second. I'm going to do this. We're going to work this out together, okay? First off, let me ask you a question. Do you have a pen and paper on you?
Yes, I do.
If you do, it's something real simple. I'm just going to walk you through this, okay, and show you why things all fall with the same acceleration on Earth, okay? So what we're going to do is we're going to write out two equations. F equals m times a. Okay. Yep. And the other one is going to be F equals big G m1 m2 over r squared.
That's the second one I was on about, yeah.
Okay, good deal. So now what we're going to do is we're going to name the M in because the force, the gravitational force, M1 would be, let's say, the object we're weighing, your 100 to 10 kilogram object, right? So that would be M1. So it would be M1 in both equations. So and now we're going to rewrite both equations to say F, or you can just add a subscript 1 to the left equation, to that first equation. F equals MA. We're going to rewrite that equation as F equals M1A, okay? So now we can eliminate M1 from both equations. All right, M1 changes anyway. We're not getting rid of it. We're just going to take them out of the equations because we could divide one side. Well, we're going to make them equal to each other because they're both equal to force. So this is what we're doing is we're making MA equal to big G times M1, M2 over R squared. All right. So now we can just divide M1 on both sides and we're left with A equals, and then are you at that point yet?
A equals G M2 R2.
M2 R squared, yes, that's correct. Now M2 is the mass of the Earth. Okay? So that is what gives us our acceleration. So do you see how we have acceleration equals the gravitational constant times the mass of the Earth divided by the radius, which is the distance from the gravitational center of the Earth, squared. Okay, so that's why all objects have the same acceleration. No matter what you change M1 to be, we can say 10, we could say 100 kilograms, we could say 20 tons. You know, we can go to whatever units we want to use because we can always convert back to the metric system. But acceleration is always going to be the same no matter what object it is, whether it's a single atom of hydrogen or whether it's a lead bowling ball. It's always going to have the same acceleration.
Technically, you've just took the first mass out by taking the two M1s.
Essentially, that's what you do, yes. But I wanted to show you mathematically so you weren't seeing that I was just saying to take out M1 on both sides. I wanted to show it to you so that way you could go back and look at it yourself and see if you find an inconsistency there.
The only inconsistency I find is that things don't fall at the same rate, but I know you're going to say, like, in a vacuum they do, so...
But, well, they do. In a vacuum, they do.
Yeah,
and see that.
And I agree, they do.
And
I
the
agree.
thing is,
Okay, but
let me just address the whole
ahead.
things don't all fall the same, right? T mentioned earlier about the sum of all forces. Now, if we take a feather that is falling, obviously it's not going to accelerate at the same speed as a lead ball, right? However, it still has that 9.8 meters per squared second acceleration acting on it. But there's other forces you need to take into consideration. And the fact that the mass of the feather is so light, it means the force is quite small, which means things like a small breeze can overcome the force of gravity. And you have to take the summation of all the forces into account. So you'd have to take the fact that the surface area of the feather and the air resistance, any wind or anything that would be causing a force that would affect something with that little of a mass. It's about summation of forces, but that acceleration of 9.8 meters per second squared is always there.
Yeah.
Okay. I know what you're saying, like, because of obviously air resistance and things like that, and
yeah.
But you know.
But nothing that you say about density can answer my question about a vacuum chamber. There is no reason for a balloon to go in a particular direction if it's just to do with density. The balloon doesn't know that it's to go down when the density around the balloon is the same at all points. The balloon has no reference. The only way it would know to go in a particular direction is if there is a force acting on it.
Correct.
I know what you're saying, but like obviously, from my point of view, it's more dense than the nothingness around it, and that's why it falls. That's why I say, like, if we could replace the air in the atmosphere with something more dense, things would fall that are less dense than that.
Okay. Let me. So you're right if you want to say under certain circumstances. Okay, under certain circumstances, things that are lighter than air will go up, and things that are denser than air will fall through the medium, through the air. But that's under certain circumstances. Okay, when you take into account the entire everything that's going on, like, or you use controls to remove the other circumstances, you're left with only one situation that happens that needs to be explained, because your special circumstances can be explained. You say, hey, I've got a helium balloon, it goes up. And I say, oh, well, that's because of this equation right here, rho VG. Okay, we get in a car, we drive forward, the balloon leans forward a little bit. I say, oh, we can explain that, rho VG. Put it in a vacuum, and I say, oh, look, it falls down. Well, I can explain that, rho VG.
I can't even argue with you because I know gravity and that does explain everything, but I don't agree with it.
Well, what is it about it that you
I
don't
think
agree
it
with?
is density.
But what is it?
Because
yeah,
obviously, like you say, like you cancel each other out on that, but like, and I understand looking at the equation, it should cancel each other out. But being that one mass is more than another, and the acceleration is times the mass, if the one mass is bigger, I still think it should fall faster because it's bigger mass times acceleration. But then you come up with another equation like which cancels out the first mass, so then it doesn't matter, kind of thing.
Huh? The point is that gravity explains everything. Density can only explain a few things.
Well, I can't see how gravity can explain the last link that I sent you, to be honest.
All right, well, should we have a look at that last link, team?
Yeah, let's do it.
Oh, good. We like this one.
I'm actually going to go ahead and pause it. Go ahead and pause it because they've hit me for this, for presenting this demonstration before with a copyright. So I'm going to just go ahead. I'm pretty sure people are aware. I can give an explanation for this without a problem. And this is sulfur hexafluoride for people that are interested in what's being shown on screen. And Rachie, if I explain anything, feel free to cut me off and tell me what I'm getting wrong. I'm not going to assume gravity here. I'm just going to explain the observation that happens. Okay, so they fill the container up with sulfur hexafluoride, which is denser than air. It displaces the air. They put an aluminum boat on top of the sulfur hexafluoride. And then what they do is they scoop out the sulfur hexafluoride with a cup, pour it into the aluminum boat, and then eventually it makes the aluminum boat sink. Is that correct?
Yeah.
Okay. Now, go ahead and explain what you need to about the observation as to how it supports your argument.
Okay, from my opinion or my perspective, I see it as obviously the gas is more dense than the foil that's floating on top of it, so that's why it makes it float, because the foil is less dense, so therefore it goes up, but it's more dense than the air, so it can't float into the air, so it stays on top of the denser gas, if you like. And then obviously as he scoops up the denser gas, and then pours it on top, it's then becoming denser all around it, but because it's so dense, the particles are packed together that it can't go around the aluminium or the foil, if you like. So it can't go around it because it's so dense and packed together, because it's a dense gas. It can't go around it, so it pushes it down.
Okay, well, I'm pretty sure the aluminum is more dense than the sulfur hexafluoride. Otherwise, it just would never sink. Or they would pour the sulfur hexafluoride in and it would just simply float at the top. The reason why it's floating, I believe, is because of the air that's inside of the volume of the aluminum. So the entire aluminum air inside of it system is less dense than the sulfur hexafluoride, because once they pour enough sulfur hexafluoride in, then that volume becomes denser than the sulfur hexafluoride around it, and it begins to sink. Yeah, would you just scoot the video up, Fight? Just show another still from the video. You don't have to play it. Keep going. That's actually not the one I was talking about with the girl. So if you can go ahead and play that one. The other one was from like the BBC, and they were doing it. But you see there, like the aluminum. Yeah, see, the aluminum is more dense than the sulfur hexafluoride. 100%. But okay, so what's your argument about this?
One second.
Rachie?
Yeah, I'm here. 1 second. Well, I'd just like to say that I was actually googling tungsten hexafluoride, which
Sulfur
I believe is basically
sulfur
there is a
hexafluoride.
tungsten as well. That's the most densest gas that you can get.
Okay.
I did Google that. That was 2,400 kg per meters cubed, but aluminium is 2,699. So it depends on the aluminium, though, don't it? Because obviously you can have strong aluminium, which is like steel, and you can have thin aluminium, which is
Are you sure that they're using? I don't know what gases they're using, but I do know at this point the aluminum would just be displaced by the gas if it was denser than the aluminum. It would just displace the aluminum, and the aluminum would rise up, unless it's being like kept there by some kind of fluid dynamics that are holding it in place. But if the aluminum is less dense, then it would just turn over. But anyway, that's beside the point. What you're trying to say here, like, how does this support your argument? Because this actually, to me, supports the gravitational argument. Gravity's pulling down on everything. Once you displace when you poured the new, denser, whatever hexafluoride that happens to be, into the aluminum boat, it increased the volume of the aluminum boat increased in mass. The volume, they didn't change the volume. They just added more massive gas, which displaced the lighter gas, and that increased the density of the aluminum boat until it was so dense that it was no longer able to be supported by the buoyant force of the gas that was in there, of the denser gas that was in there.
But it didn't change volume, and it was floating to begin with. And they say, the volume is displaced, and if it displaces enough, then it'll float. The volume didn't change, so it should still float.
No. Okay, you're right. The volume didn't change. Okay, so you'll agree that when she scoops the cup in there, she's scooping out the hexafluoride gas, correct?
Yep.
Okay, so and that's more dense than the atmosphere around it, correct?
Than the air, yeah.
Okay, so when she pours it into the into the aluminum boat, it displaced the lighter air and filled it up with denser air, correct?
Yeah, correct.
Okay. So as it filled it up with denser air, it increased the mass without increasing the volume until it was more dense than the sulfur hexafluoride or the hexafluoride underneath it.
I'd say that the gas is pushing it down, pushing down on it, because the gas is more dense, and obviously it wants to go down because it's more dense, so it's pushing that down. If you like, the gas has more force than what it does to push the boat, so to speak, up.
Okay, so if it was like that, then that's what I was saying. Unless it was designed like hydrodynamically designed to float on water, on fluid, then the boat itself would tip over once it reached a point where there was so much weight on the inside that it would just cause it to tip over, and the buoyant force would push up on the aluminum boat, and the aluminum boat would rise to the top. I mean, there's certain circumstances where you could get this to float, but as you can see, they didn't design something that's just seaworthy here. They're just using it as a demonstration. Now, the fact that they could be really, really close, right? They could be really, really close, and it still wouldn't change what we're seeing here. Now, is there a description in that tells you what the gas that they used is? Oh, we'll look this up.
Have a look a sec. This is sulfur hexafluoride that they used.
Sulfur hexafluoride, all right.
So what was that? You was trying to say it would tip over if what?
If it became unbalanced. Like if it wasn't balanced going down inside of there.
But what about when a boat gets water on and that's unbalanced, that still sinks and it doesn't tip over?
Yeah, boats are designed for that.
Okay.
All right. Hold on 1 second. I have to do a conversion real quick. I mean, right now we're just getting the the densities. I mean, you can continue on with your argument. I'm just converting the density so I can make sure. Rachie?
Yeah.
Did you hear me? You can go ahead on continue on with your measurement if you want. I mean, with your argument regarding this.
Yeah, I would just say that it fell down basically because obviously the gas is more dense, so it doesn't go around it like it would a helium balloon because air is less dense, and the gas in that is more dense, so therefore it's pushing it down. It can't go around it because the density is more close together. So that's basically what density means, that the particles are more closer together. So.
Okay.
And mass,
no,
yes,
density.
myself, I would say mass
means...
is weight. So obviously it's adding more mass on, which is adding more weight too. So.
Okay, so I guess I'm still kind of confused as to what your argument is here, because I think that everything that you're saying can be explained by gravity. I mean, there's nothing you're saying that's not explicable by gravity and the buoyant force, correct?
Well, how would you explain gravity on that last one? Because you're saying that add more mass, then therefore it goes down.
Well, it's the sulfur hexafluoride is more massive than the atmosphere that's sitting inside of the boat.
I agree, but I think it goes down because the gas is more dense and it's pushing it down because it can't go around the boat, so to speak, so it pushes down on it.
Hold on 1 second. You said, I'm sorry, you said what now? That you didn't think that I wasn't trying to not pay attention. I was looking at something. I'm trying to get the correct conversion for the densities of the sulfur hexafluoride and the aluminum because it gives it to me in 2 different units. But what were you saying just now?
That basically I think that it goes down because the gas is more dense, so it basically pushes it down because it can't go around it because the particles are too close together. That's why it's more dense, because the particles are closer together, and therefore it's pushing it down.
Okay, now if it was okay, so what about the particles underneath it that are pushing it up? Shouldn't it have been supported already? There was more particles underneath. You'd have to compress those particles more to get it to move in that direction. So why would it not just have stayed afloat?
Well, you say that there's more particles underneath, but obviously they scoop some out, so then it tries to like fill the area. So the top, when it scoops them out, and there's some at the top that goes back down into that area. That when
it drops, it's still sitting at the top when it drops completely.
I'm not sure about that, but still, it's more dense, so it will push it down anyway.
Okay, I guess I still just don't understand what you're saying.
Yeah.
I mean, it's not anything different than we would expect
this
from
supports us instead of you.
Yeah, this to me does not exclude gravity from explanation. We can use gravity to explain the observation that you're showing here.
I agree that these are like there's almost like there's 2 different ways to explain it, and obviously they're both like. Well, I think there's 2, and there's 2 different explanations for it, and they're both experimental ways of explaining.
I'd agree with you, but then we'd both be wrong. So.
Okay, so let me see. All right, the conversion that I'm getting is 2.7 grams per cubic centimeter is 2,700 kilograms per cubic meter. So the density of aluminum is about
aluminium
400 times greater than that of the sulfur hexafluoride. So the combination of the mass, yes, the aluminium. I'll try to say it like you guys, just to appease y'all tonight. Okay.
Properly, you mean properly?
Yes, I'll say it to make y'all happy.
Colonists.
Okay, 2.7 grams per cubic centimeter is the density of aluminum, okay? The density of sulfur hexafluoride is 6.17 kilograms per meter cubed. Now, when you do that conversion, 2.7 grams per cubic centimeter comes out to 2,700 kilograms per cubic meter. So that would mean that it's about 400 times more dense than the air around it, than the sulfur hexafluoride. That's why it sinks, because the total density of the aluminum boat with the sulfur hexafluoride inside of it is greater than the density of the sulfur hexafluoride underneath it. Now, when you start out and you just have air in it, it's not. It's not
So
more
what's
dense
the
at that point.
density of sulfur hexafluoride?
2.7 grams per centimeters cubed. I'm sorry.
And that would...
I'm sorry. That was aluminium. It's 6.17 kilograms per meter cubed.
6.1 grams.
Kilograms per meters cubed.
6.1 kilograms.
Yes, per meters cubed.
Per meters cubed.
So kgm3.
Yeah, kgm3 exactly.
So that you're telling me that the gas is a lot less than aluminium?
A lot less, 400 times less dense.
A lot less.
Okay, well then it can't be density then, can it?
No, it can't be.
Well, no, obviously it can't,
Gravity's
because
a
if
thing.
it's like if aluminium's more dense than obviously the sulfur hexafluoride or whatever you call it, then yeah, then it can't be. Obviously that ruins the density of thing, don't it? But the problem I still have is, why did I know the cube would float without using gravity or anything?
Because you made the assumption that there was already a downward force and that all objects that are more dense will go down. That is what gravity says. Gravity actually just says all mass will go down. And then when you take that equation that you and I worked together on to say that, the F equals ma, converting that to F equals G1, or big G times M1, M2 over R squared, when we did that and we showed the relationship between those two, and we said, okay, the Earth pulls on everything with the same acceleration. All right. Now the force that it pulls on those objects with is equal to that acceleration that they all share. Okay. So we can really get rid of acceleration, right? At that point, we can just say that the force is proportional to the mass. So the bigger an object is, the more, or not the bigger, but the more massive an object is, the more force is going to be pulled down with. The more force it's going to have as it accelerates down. So in this situation,
with the cube though, I wasn't thinking of that. Like, obviously everything in the cube is more denser than the mineral oil. That was only 870 kilograms meters cubed, and obviously every other tin, aluminium, copper, lead, glass, and polycarbonate was all more denser. But I still knew it'd float from my equations, and that didn't have gravity or acceleration in it.
well,
So I
because
don't
you
really
assumed,
understand that.
but here's the thing: you assumed gravity and acceleration already without even knowing you did. Even if you don't want to call it gravity, you assumed acceleration. You already assumed everything would be going down. For if an object is at rest
No,
and it
because I knew
begins to
it'd
accelerate.
float.
No, hold on.
It
That's
didn't
why.
go down.
But that's why I asked you in the thought experiment. I said, let's hold this above the water and let's drop it in there, or above the mineral oil, and then let's drop it in there. So we're not starting in the oil already. We actually start out of the oil, enter into the oil, and let natural processes take over. Okay, so what you did is you immediately assumed that all things are going to go down because they just go down. That's why there's, like when we argue that point, we're like, no, you're making the assumption gravity is there and then saying that gravity is not there, but you already made the assumption gravity was there when you said that all objects will accelerate towards the ground. And you've said that several times tonight. At all objects,
Well,
and I
to me,
agree
I
with you.
says that, like,
Go ahead.
sorry, carry on.
No, I was going to say, I agree with you on that. All objects will fall to the ground, especially under controlled environments like in a vacuum. And if it's not a controlled environment, then we have to take in other forces. Because the only reason, like when we say force equals mass times acceleration, right? If you and I put the exact same amount of force pushing in opposite directions of each other, it's not going to accelerate. Whatever object we're talking about, we could be, a big medicine ball on the ground. You're on one side pushing with 10 newtons of force. I'm on exactly the other side pushing with 10 newtons of force. How far is that ball going to roll? It's not going to roll anywhere. We're both pushing equally in opposite directions. This is why we have to account for all forces present when we're making assumptions about things. When you want to talk about the helium balloon going up, are you also taking into account the forces that are due to the buoyant forces that are present inside of our fluid atmosphere? If you're not, then you're doing yourself a disservice. If you can still explain why the balloon goes up and explain gravity at the same time, or without explaining gravity and without giving, explaining some other reason for the direction of motion to be down, then you would have something. You'd have a point to argue. But until you're not accepting in your demonstrations, you're just simply not accepting that there are other forces involved that cause the helium balloon to go up.
I think we just need to acknowledge that she accepted that density can't explain a lot of things, especially with the demonstration on screen.
Yeah.
Density doesn't have the predictive powers that gravity does, and that kind of just ends the discussion.
It's also the same
so
question
Rachie,
can be said. Well, at least from your point of view, you need to reevaluate your position because we're not asking you to believe gravity tonight. We just need you to understand that your current explanation is incorrect. And there's there's demonstrations and explanations that do explain why your explanation is incorrect. But we're not saying believe us. We're just saying what you said was wrong. Reevaluate what you're saying.
No,
and see
obviously
what you
I can
come.
see from that last one that obviously because she says the aluminium was obviously more dense than the gas, then it should have fell and it didn't. So obviously it's not density in the air around it and things like that. So.
But to an extent, it is density. That's the other point to take from this. This is why a flat earther gets confused by these concepts, because it is density to some extent. Okay, because as we saw in here, when we poured the sulfur hexafluoride into the aluminum boat, it displaced the lighter air, thus increasing the density, and at some point, the boat sank. So there is something going on with density, but you cannot discount the contribution that acceleration adds to that fact. And the only acceleration that's going on in this is the acceleration of gravity. The same acceleration that exists when you drop a tennis ball to the ground. You don't have to accept that it's gravity, but you're going to need to explain that acceleration without using density.
No, obviously I can't argue with you on that last point because that last link obviously it proves that it's not density. But again, I still don't understand how I could know just by times in the density by the volume of the sides that how that cube would float or not, because I didn't use any gravity or acceleration. All I used was the density times the volume of the sides, and then added the density of the air times the volume of the inside, and added that together to get the mass, and then obviously I said how much it would displace, and then got the mass from that, and obviously I knew it would float, but I didn't use no gravity.
Still assumed you still assumed a vector, even without realizing it. You still assumed something causing a vector, giving it a reason to go up or down, and you don't realize that you've done that, and that's the thing, right? But I think
I assumed it by mass. If the mass displaced is more than the mass of the object, then it'll float.
Yeah, but again, you just assumed the direction. You didn't explain why it would float up or down. But honestly, I think we should move on from the gravity/density thing now. I'd like to show you a brief video as evidence from our side and see if you can explain this observation for me. All right? Do you want to make your full screen a sec?
Okay.
Several observations, actually. So the Earth's flat. Can you explain all that?
Well, yeah, two arguments I have for that. Well, not flat, level, because water is level. That means it's more always horizontal, perpendicular to the
Rachie,
ground.
hold on. The word level means conforming to the curvature of Earth's surface. So, yes, it's level. But explain the fact that you go against it, you being a globe and you're a flat earther. If we have all these images from space, it's things that need explaining.
It's if
And
you
you
believe
can't
they're
just
real,
go,
though, ain't it?
it's
Like, obviously,
fake.
we know a lot of things can be faked. So obviously, people do think
Yeah,
that
but
they're
that's the
fake
thing.
because a lot of things
You
can be
have
faked.
to just assume that it's all fake. And that doesn't fly with me. You can't just say, well, it could be all fake, because there's so much of it, and there's dismissing it because it could be fake is a very intellectually dishonest position to have. So what is the explanation? Well, how come we can every 10 minutes get a fresh image from space from the Himawari satellite that matches with the real-time information on the ground? Come on, what's the explanation for it?
Well, you say it does, but I haven't actually experienced that yet. Somebody has sent me that satellite picture, but I haven't actually looked at it every 10 minutes. And obviously, it's over Japan and or the other side of the world, so I
There's a
can't actually
channel
tell
called
if
Wade's
how
Underworld.
it's measured, right?
There's a channel called Wade's Underworld that has actually done exactly what you're asking for there. He lives in, I think, Eastern Australia, and he took images of Himawari at real time and compared it to the actual cloud images of what he has, and it all matches up, and it does. And with the Himawari satellite, I think it was in 2015, 2016, they saw some bushfires in Mongolia heading towards a village, and the only way that they could have spotted it is from a satellite in space, and they managed to use that real-time data to warn the people in the village to move, otherwise they would have all died, and it all matches up. So without just going to
Well, I
the
do believe the
default,
satellites
it's
up
fake,
there. I've seen
what's the
the
explanation?
launches of them, like, so I do believe there is satellites up there.
Yeah. If satellites are up
But
there,
whether
then
they're on a
the Earth
balloon
can't
or
be
anything,
flat.
I don't know. Because like I have seen one fall in Brazil and they recorded it, and there was like a balloon attached to it. So
So there is an American satellite called GOES-3, or the Geostationary Environmental Operational Monitoring System, and it was in operation for 32 years. Okay, and it was in a geostationary orbit, which means that it has to be 22,236 miles above the Earth's surface and have a tangential velocity of 1.91 meters per second squared. There is no balloons that could, under all known laws of physics, reach those heights and speeds, let alone maintain them for 30 years.
how did they?
So
Are you
it
trying to
can't
say
be
they
balloons.
didn't? But what about
No, I'm
the balloon
saying
that
that
was
it can't.
attached to it?
I'm
Was
saying
it
it can't be
missing the
balloons.
balloon?
Yeah, well, that's the thing. There is some temporary weather monitoring systems that are mounted on balloons. Right? No one's denying that those are things, but no one is saying that they are satellites. Okay? They're just a completely different thing. There is actual satellites that have been in operation for over 30 years, over 22,000 miles above the Earth's surface and moving at 1.91 meters per second squared for over 30 years. Balloons could not do that.
I
So
agree.
it
Balloons
can't be a
couldn't do
balloon.
that. But
So
I
it
have
can't be a
seen
balloon.
videos of balloons going down, but you're saying they're different to the satellites.
Yeah, no one's denying that there are temporary weather monitoring systems that are mounted on balloons that go high up into the atmosphere, but that's not satellites.
So why don't they just put them in orbit and not have a balloon?
Because there's certain things that a balloon could measure from within the atmosphere that a satellite maybe couldn't from without it. They use a lot of them to measure the air currents and stuff in hurricanes, so they can position balloons within changing weather systems to monitor it from within. You couldn't do that with a satellite. You could only get an external picture. So there is reasons to use a balloon rather than a satellite in certain occasions. Balloons are a lot cheaper. That's one of the reasons. If you need to study a particular thing and you've got a choice between putting a balloon up or putting a satellite up, the difference is going to be millions and millions of dollars or pounds, So why would you go with the more expensive option when you could get the things that you needed from a cheaper option?
True, but why would you waste 5 million or billion sending a space probe to the sun when you can send people back to the moon?
because we would also like to learn about the sun. For instance, the Parker Solar Probe has taught us many things about the sun that we didn't know before. It may have a lot heavier elements towards the surface than we thought before. So the Parker Solar Probe and other solar probe missions have taught us things about the sun. But we also are now going back to the moon, obviously with the Artemis missions. Probably not in 2024 due to COVID screwing a bunch up. I'd say 2026. But the plans to go back to the moon are there, and if Elon Musk has his way, we'll have 1 million people on Mars by 2050.
Bringing up Elon Musk, do you really believe he drove his car in space?
No, he didn't drive his car in space.
Wait,
he
what?
Sent the Tesla up as he sent the Roadster up as a test payload.
I'm sorry. Can you repeat that?
I know. Okay. Drove his car. No, fuck me, Rachie. No, the reason that Elon Musk sent up his Roadster was to test the payload capabilities of the rocket systems they were designing. It was probably a bit of a stunt, to give his company more value and stuff, but it also demonstrated that the payload could indeed carry something that heavy into space.
Okay, but to me it looked like the car was literally flying around space, and like it had no thruster or anything to push it through the vacuum of space. So like, how could it fly through space?
Why would it? It was already It was already traveling at a velocity due to the fact it was in a rocket when it was released. They launch it into space and it's going a particular speed. Then they release it from the payload system, and then it maintains that speed. It's not going to just stop for no reason. That would require...
So they don't need to use any kind of boosters or anything to get to the moon because it'll just carry on with that speed anyway.
Yeah, there's nothing there to like accelerate it in the opposite direction.
Yeah. So if talk about, like, for instance, the Apollo missions, like what they did was they once they got into orbit around Earth, they orbited Earth a couple of times to use the gravity of Earth to increase their speed. And then they coasted to the moon for 3 days. Only when they got towards the moon did they then start using fuel again to achieve orbital insertion around the moon and stuff, from then to launch the LEM to the moon's surface. So once you're in space traveling a certain speed, you don't then need to use a bunch of fuel to keep going that speed. If you wanted to slow down or accelerate, then you would need to use extra fuel.
So we don't need no fuel to go to Mars?
No. Well, it depends on...
fuel to escape Earth's gravity and stuff.
Yeah, and then they're going to need fuel to get to whatever acceleration or whatever velocity they need to get to have. And then they'll need some way of slowing down when they get there. But once they reach the velocity they need to be at, there's simply nothing to slow... there's no like molecules of air to slow them down. They just continue traveling at that velocity until, a force is applied. Either they hit something that slows them down, or they, fire off engines or whatnot to slow themselves down.
Okay, so when was satellite to put in space? Like the first one for GPS?
When
was the first GPS satellite launched? I believe
roughly.
94. No, I'd have to Google that information. Let me have a look.
Okay, so what's after gravity? Because I think we're done talking about gravity for the evening. Unless you got something else you'd like to present. Go ahead.
Obviously, the Chinese apparently found some kind of, I can't remember what it was, glowing material or substance on the surface of the moon, on the dark side of the moon. But they says that they couldn't get there before because they needed to put a satellite out past the moon. But then I don't understand how they could have planes and fly to the opposite side of the globe when they didn't have GPS, and yet they're saying they couldn't land on the dark side of the moon because they needed a satellite so that they could translate to their position, kind of thing.
Sorry, Rachie, but what the fuck did you just say?
I'm a bit confused too.
Okay, so basically, I read on the news.
All right. Go ahead.
You still there, Rachie?
Hello.
Is she still connected?
Hello.
Yes, we could see you.
Oh, hello. Yes, you're back.
Yeah, basically what I was trying to say is that, like, recently I read that they found this substance on the moon, the Chinese did, that was glowing or something. And they says that the only reason they managed to land on the dark side of the moon was because they put a satellite out past the moon, which could translate to the position that they was in order to land on the dark side of the moon. But then I don't understand how we could use planes to land on the opposite side of the Earth if we are a ball like, and land on the opposite side of the Earth without satellites being up there to translate our position to the Earth, almost like.
Okay, so trying to land something on Earth and trying to land something on the moon are like two completely different levels of difficulty. So we're pretty, even if we had a good topology of the opposite side of the moon at the time when all this was going on, they would have still needed to communicate, just like the Americans needed to communicate with the control center, Houston Control Center. Like they still need to communicate with each other. If there's no satellite on the opposite side of the moon, it's called the dark side of the moon because it's a dark side of communications for us. Because the moon, relative to us, it always shows the same face. So if you have somebody on the opposite side of the moon, let's say you have a moon base on the opposite side of the moon, you wouldn't be able to communicate with the people on Earth because there's no way to send them a signal. You'd have to send the signal through the moon. So you have to have a satellite that's up beyond the dark side of the moon so that you could send the signal to the satellite and the satellite could send the signal back. They probably, when they say they don't have a satellite on the other side, they probably mean for like safety purposes. They can't guarantee a successful mission or even like the higher probability of a successful mission without some kind of communication with their control center and their astronauts who are flying the vehicle.
Yeah, they do have a satellite out past the moon now, but like what I meant was how could they fly from one side of the Earth to the other side of the Earth without a satellite on the other side of the Earth? Because they have that problem with the moon. They should have that
because
problem
we
with
had
the Earth.
maps before we had satellites. I mean, you might as well ask, how did the Vikings sail so far without GPS? Like,
but that's
the
different
question
to
really doesn't make any
flying
sense
a
to me,
plane.
Rachie.
But
yeah, why
like
would
going
you need
across the ocean is
GPS to
different.
fly a plane? Yeah, but okay,
No,
so
isn't that what they use
what
at
if
the
you've
minute,
got to
though?
come? Well, at the moment, GPS is the large part of navigation. But for instance, imagine you don't have any electronics or anything, and you want to get from the UK to America. All you need to do is have a compass in your plane and fucking fly due west. You know?
Yeah, but there is no really
It's
west,
like,
is there? I mean, there's a North Pole and there's a South Pole, but there's not actually a West Pole or a
what do you mean there
East
isn't
Pole. So
really
you can
west?
go like you can't go
Wait,
east.
sorry.
Like once
What do you mean you can't go east? Of course you can go east. Like
if
look
you
at my
keep
screen
going
right
east,
now.
you'll keep going east.
Hold on, Rachie. Look at my screen right now with my globe. Right, those letters are flying west. Right, they're not going to stop flying west. They're going to go west around the globe all the time. If they went the other way, they'd be going east. It's as simple as that.
Yeah, I agree. But when you go north, you get to the north, and then if you keep
West
going,
Pole.
you go south. Like whereas if you keep going west,
That's
you'd keep
why we
going
have a
west. You'll
north
never
and-
say east.
Yeah. No one's saying we have a west pole, but to say there isn't really a west is a very stupid thing to say, because the fact that we have a north and south then allows us to have a west and an east.
Yeah,
But there's no
north.
west pole. Like you keep going west, and it'd always say west.
Of
but
course
if you
there's
went
no
north,
west
it would
fucking
always say
pole.
north. But if you always went north, it wouldn't say north
Right,
all the
but-
time. It would say south once you
Right,
get to the
right.
North
When
Pole.
you, when you
it'd
get to
go
the
down
North
south.
Pole, every direction
That's
is south,
because
and
we
at
have
the
a
South
north
Pole.
and a south pole.
Yeah, that is correct. But west, what west means is that it's just a relative direction. It's a vector. It's in what direction is orthogonal to the line that connects north and south. Which one of these lines are 90 degrees. They form a 90-degree angle. At that point where it forms the 90-degree angle, the line that it makes is one side of the line is pointing in the west direction, and the other side is pointing in the east direction. So it's just like
But you
a
don't find
relative
it weird that
direction.
you can keep walking west and it'll always say west, but if you walk north, eventually it'll say south.
Yeah, as long as you're heading west, yes, it will always say west because it's
I find
relative
that
to the
strange,
north. It's if
But
it,
if you always walk north, it'll never always say north. Eventually it'll say south.
okay.
Yeah, that's because we have a north and a south pole. We don't have a west or an east pole because west and east are directions relative to the north and south pole. Because we have a north and a south pole allows us to define a direction as west and east in relation to the north and south pole.
Okay, so let me ask you a question. How do you define north? How do you define north?
On my compass.
No. I mean, like, if someone said, "What is north?" Like, explain it to me like I'm 5 years old. What's north?
It's I don't know. It's on the compass and it says N, and then you can go to that direction and you go in north.
Okay, if you didn't have a compass and you still needed to tell somebody what north meant, what would you tell them?
Apparently,
you're not really
the
explaining
Polaris
north,
Star,
you're
but I
just-
haven't actually seen it.
No. That's the North Star. What does north mean? If you're on the surface of the earth and I say head north, what does that mean?
Without a compass, I couldn't tell you.
Well, I mean, if I didn't say, what are you going to do? I said, what does it mean? If I tell you to head north from any point on earth, what does that mean?
Go in a certain direction.
Okay, and what defines the direction you're going to be going in? The North
The
Pole?
north.
The North Pole?
Yeah.
Okay, so at any point, you can't keep going north at the North Pole because you're at your destination. Okay, that's all that means. Okay, so at
But
the
why do
North
we have a
Pole,
North
you
Pole? Is that
cannot
because of the
continue.
magnetic?
Well, it just means
Yeah.
that if you keep following the straight line, the same way you do when you're going west, you're always going west, right? Like, doesn't matter which, you never stop, you're always going west because that's how you chose to define it. We can choose to define it, by saying going relative to the direction west, always going 90 degrees with, I guess, like, that's why it becomes tricky while we're discussing, while you have poles, okay? We have poles so that you can give yourself a relative direction. All right, we can't have west. If north and south do not come together at a point, then you can't have west and east. All right, do you understand that, right? Because at one point, once you go over on the other side, west then becomes east because it's going in the opposite direction to which way is north to you.
So AT2
Yeah, I know what you're
Productions
saying,
has
but we
said
also
it like
have
this.
two norths.
Right, so one is perpendicular to the magnetic field, east-west, and the other, north-south, is parallel to the magnetic field. Does that make sense?
Say that again, sorry.
So east to west is perpendicular to Earth's magnetic field, whereas north to south is parallel to Earth's magnetic field.
No, I disagree.
Why don't you understand that?
Parallel isn't parallel to the ground. So if you had the ground, you'd have something straight along
What?
above it, going straight.
Parallel just means along next to.
They're parallel to
What?
each other,
Wait.
so they're going in.
Yeah,
They're going in like two
north
straight
to
lines, like
south
train
is
tracks.
parallel to Earth's magnetic. North to south is parallel to Earth's magnetic field, which runs north to south or south to north. That's where
I
it
thought you were
emanates
saying
from
it
the
was
north
east
to
to
the
west.
south. Yeah, well, that would be perpendicular to Earth's magnetic field.
Oh yeah, I thought you meant the other way around.
No. East to west is
Yeah, I know what you're
perpendicular to
saying
Earth's
now.
magnetic field, whereas north to south is parallel.
But it still doesn't.
Yeah,
It still
yeah.
doesn't get the point I'm trying to get across. Okay, so like west is always in one direction on the globe, whether you're facing north or south. Okay, so like if you're looking north, then west will be to your left. If you're looking south, then west will be to your right. So the purpose of the poles is to to keep that consistent. If you didn't have the poles, then when you were going in one direction, left would be to the left of you, and then once you crossed over the point of rotation, going west would be to the right of you. If you didn't change your orientation, if you didn't say, well, now I'm facing south instead of facing north. But on west, you can only face west. You can never get to a point where you look like you're facing west from one perspective and look like you're facing east from the other.
Yeah, I know what you're saying. I understand that now that you're saying it, but like at first it didn't make sense. Like you could just keep going east and it would always be east. But I know what you mean now. Like.
Yeah, and Jared's right too. It's the directions are basically explaining, a parallel cross section of the rotation. Of the angle of rotation. If we're not using compasses in here, if we're just using the North Pole as to represent in what direction north is, then the lines of latitude or lines of latitude are just simply cross sections of the axis of rotation all the way up. 90-degree cross sections.
I know what you mean, but I still don't agree that it's a ball, like a globe Earth.
And what would be your reason for that?
Explain all the images that I showed you.
Well, they're images. A lot of people will say they're fake, but even if they are real, like I can't take them as real because things can be faked. But like obviously, you even said in your video in the last one that like there's no forces acting on that camera inside the water ball. Like.
Yeah, because the ISS is under freefall, right? Which means that there is no gravitational acceleration acting downwards on the water within the thing that's in freefall because it's already accelerating towards the ground. So that cancels out the gravitational acceleration, which means the net sum of forces on that spherical bit of water with the camera inside is zero.
Okay, and I can agree with that, but at the same time, if that's how it acts and we pretend like the camera is the Earth and the circle is the water around it, then obviously once you add gravity in and you add that as a force, then it should act.
Oh no, I wasn't saying that. Don't get me wrong. I'm not saying that is equivalent to Earth's gravity. I was just simply making the point that when water is under zero forces, the natural shape, because of hydrostatic equilibrium, is for water to be a sphere. So when Eric Dubé constantly says water is flat, he's wrong, because the natural state, hydrostatic equilibrium with the net sum of zero forces, is for water to be a sphere.
But once you add the force of gravity, then it would no longer be a sphere?
Exactly. That's because there is no longer a net sum of zero forces. Water conforms to forces
sphere
acting
around
on
the
it
Earth?
because of gravity.
But you just said it was a sphere without gravity, without any forces. So once you add gravity, it should no longer be a sphere, so it shouldn't curve around.
Well, gravity pulls towards the center of the Earth. At every point on Earth's surface, there is a vector pointing towards the center of Earth. So water will naturally curve to the surface of Earth if every point along the surface is pointing towards the center. Water conforms to forces acting on it, right? It's as simple as that.
So you're saying there's no gravity, like technically on the International Space Station, all the forces end up with zero?
Yeah, the net sum of forces is zero because the International Space Station is in freefall towards the Earth.
So technically, if they put a big ball, which represented the Earth, and a small ball, which represented the International Space Station, they could technically throw that over and it would just keep orbiting it.
Yes.
Yeah.
Really?
Yeah, you're talking about like in space, right? Like away from the Earth. You're not talking about on Earth, right?
No, on the station, like if they had a bigger ball and then they had a smaller ball and they threw it around it, it should keep circling.
Well, it would need to be extremely massive.
Right.
Yeah. The mass
you couldn't
is a
just
part
do
of
that
that
on the International Space Station. Yeah.
Like,
sorry
give me an idea.
there.
No problem at all. Give me an idea, just real quick. How big of a ball would be the big ball that would need to be orbited? Okay, just give me an idea of how big you would think that they would make this ball, and out of what material they would make it. Like how much? You don't need to give me a material. Just say how much mass the object should have, and what the diameter of the object would be.
Well, I suppose if it's meant to be, mass attracts mass, then I suppose the more density and the more volume would be the better to making it something smaller volume. Well, still a bigger volume because obviously mass attracts mass, so you need more density and more volume of both of them really to attract each other. So.
Well, more
I'm not really sure
density
how big
is
that would
not
be, but
consistent. Well, more density is not consistent with more volume. More density would mean either less volume or the same volume, or like the same mass with less volume, or the same volume, with more mass. So one of those two would not work with the other one.
what I mean is like if
I
had
agree
more
with
mass,
you. So just do me a favor. Give me a weight to a ball. And you can do kilograms or pounds, it doesn't matter. Give me a weight to a ball and a diameter of that ball that you would want to see this experiment on.
I've never actually thought about it. A weight of a ball, well, it'd have to
give hypothetical.
something quite big.
Yeah, it would need to be quite big, you're right.
But it'd need to be fit on the International Space Station in order to do it, so
Agreed.
I'm not sure how wide the International Space Station is, but obviously something smaller than how wide that is. And
well, give me a
something
weight.
which is as dense as possible.
Okay, give me a weight.
I'm not sure because I don't know how.
You want to do 200
big a
kilograms?
mass
You want to do 200 kilograms and 1 meter?
if that would fit on the International Space Station.
I mean, I'm sure if something had we'll just say a radius of 1 meter with 200 kilograms.
Okay.
Okay. So let's find out what the acceleration would be under that circumstance real quick. Let me pull up my calculator. All right. I need to download my other calculator before too long. I'm not gonna do it tonight, but I'll still get the.
Is it okay if I just pop to the toilet for 1 second?
Yeah, go ahead. I'm gonna calculate that value real quick. Okay. So go ahead.
Okay, thank you.
Let me go to. I'm gonna find a better scientific calculator than the one I'm using. Hold on. Okay, there's one right there. What's big G? 6.7 times 10 to the negative 11th, I think. Yeah?
That sounds about right.
I need to know.
2 secs.
I think it is, but I need to know.
6.674 times 10 to the negative 11.
Okay. Wanted to make sure. And it's mass of the Earth in grams, right? Oh, wait, no, we're using 200 kilograms, so it would be 200,000. And we are dividing it. Hold on. Okay, never mind. It's 200 kilograms. Kilograms are the unit of mass, not grams. Okay. We'll wait for her to get here.
Okay. Jesus.
Because I'll tell y'all, and y'all can tell me if I'm right in the chat, but the answer I came out to was 1.34 times 10 to the negative 8 meters per second squared.
Yeah,
that would be the gravitational acceleration at the surface of that 1 meter ball.
What's that?
Okay, so go ahead and pull out your calculator right now.
I haven't got one. It's on my phone and I can't.
Okay. So here's what I did. We did big G, which is 6.7 times 10 to the negative 11th, times the weight in kilograms, which is 200 kilograms, divided by r squared, which is 1 meter, and that I believe it's in the SI unit is in meters, so it's just divided by 1 squared, which is equal to 1, and that gives us an acceleration of 1.34 times 10 to the negative 8 meters per second squared. Okay, so that's a really, really, really small acceleration that you're trying to display based on, just the like a local experiment to do. Like you would have to increase the mass by orders of magnitude, or shrink it down by several orders of magnitude. You'd have to shrink down that ball still, or make it much, much, much heavier. Because it's not necessarily just about the density; it's also about the mass, the amount of mass. That's why the Earth has a gravitational acceleration. It's not just because of the size of the Earth; it's also because of the mass of the Earth. If the Earth was much bigger and had the same mass, we'd have less gravitational pull on the surface. Or if it was much smaller with the same mass, we'd have much greater acceleration at the surface. But it still is like, if it wasn't for the mass, then we would have no acceleration. So it's kind of like one of the key parts to it.
Do you agree mass is still density?
No, mass is not density. Density is mass per unit volume.
Times volume.
Well, yeah, it's mass is density per unit.
How
mass
much
is
density
times volume, yeah.
Volume?
I'm sorry?
So it's still density.
Okay, so if I told you that your volume was 1 cubed, right? 1 meter cubed. And I said your mass inside of the volume was 1 kilogram of mass, all right? Then your density would be 1 kilogram per meter cubed, all right? So if I told you that the volume of the gas was 1 kilogram per meter cubed, and I have a meter cubed of it, then you can tell me how much the mass is going to be. They're individual parts of the whole system. All right, so you can't have density without mass, or without volume. You can't have density.
But
so
density is mass because it's how much density is in the volume. So it's like how close they are times the volume.
No, I think mass. No, mass is an underlying property of energy. Okay, so if something has mass, basically it's not moving at the speed of light. That's just pretty much the way you can explain it. If it has mass, then it's not moving at the speed of light, which is most of what you and I are talking about right now, is the mass that doesn't move at the speed of light. Okay, so mass is just...
Does matter?
No, not necessarily. Not necessarily.
That's
matter is something... I mean, that's a way of explaining it, yes, but it's not the best way to explain it. Because we have calculations. Mass is just the relationship really between... mass is energy that's not moving at the speed of light. That is the easiest way to explain it to anybody out there. If you're not moving at the speed of light, you have mass. What mass is it's just the amount of energy that you have in your system. So the relationship between the amount of...
Does light not have mass?
No, light does not have mass.
I think you should Google that, because light does have mass.
No, it doesn't. It has momentum, but it doesn't have mass.
Try Googling it, say, does light have mass? And I guarantee you it'll say yes.
I've got to at least try. I'll appease you.
So the first thing that comes up, does light have mass? Light is composed of photons, so we could ask if the photon has mass. The answer is then definitely no. The photon is a massless particle, according to the theory. It has energy and momentum, but no mass.
Yes, no mass. Like I said.
I could have swore I read something with mass. I could have swore I did.
No, it has energy. It has energy, but no mass.
No, I could have swore I read something that says that it has mass, but I didn't understand how it could have mass, because obviously wind has mass, you can feel it and things like that, but obviously you can't feel, well, you can feel like temperature, but that's about it, like when it gives off heat.
Yeah. So really, matter is anything that's not moving at the speed of light, would be considered matter. Mass would be the relationship between energy. Mass would be the amount of energy divided by c squared when an object is at rest. So you have to, like I said, there's a lot. It's a really hard explanation when you talk about something that, when you're asking to explain mass, because mass is just energy that's not moving at the speed of light. So when you ask for matter, matter is just mass that, again, is just energy that's not moving at the speed of light. You would talk about it in its like touch form, like, oh, this is, I can touch it, it's matter. But if you wanted to explain how much of that energy was in that object, then you would explain it in terms of mass, not matter.
Okay, I'd just like to ask, what's c squared? I've never heard of that one before.
Speed of light.
Speed of light squared.
C squared?
Yes.
Yeah.
C squared.
I thought the speed of light was m equals mc squared.
What?
Isn't it something like E equals mc squared? No, E equals mc squared.
Yeah, E equals mc squared is the equation to describe how what energy is. Energy is described as mass times the speed of light squared.
Okay, so then the speed of light is, I forget now, 2,000 and odd miles per hour.
180,000 miles per second, 300,000 kilometers.
1 divided by the square root
miles
of epsilon naught times mu naught.
What he said.
Okay, and that's how light can travel forever.
Yes.
Yeah.
There's nothing to
naturally, yes.
Light is a self-propagating wave. Unless you have something to stop the self-propagation, it will continue on forever.
So can a flashlight be seen from, say, 69 miles away?
It depends on how powerful the flashlight is, I would say, and what the ambient light around it was. How dark, in other words, how dark the room you would in.
Yeah, got in the way.
I mean, there's you just asked me if a flashlight from 69 miles could be seen. You didn't say if I have a flashlight sitting on the surface of the earth at 6 inches above the surface, will you see it, under these refractive indexes? Then I can answer that. But a flashlight from 69 miles away, if it was strong enough and there were no obstructions, yes, you could probably see it. And it was dark enough.
Yeah, that was probably a trick question, to be honest. But another thing I don't understand is how you can see like 0.4 degrees, but then you can't see 1 degree. Like some people say to me, oh, well, how would you notice 1 degree of a tilt of a building, for instance, on the curve of the earth? But like we can only see from eye height like 0.04 degrees, and I don't understand why 1 degree of a tilt of a building is barely noticeable, but we can only see 0.04 degrees. Shouldn't we be able to see 1 degree, which is like 69 miles?
Well, okay, so this is tilting directly away from you, right? So let's say you had 2 popsicle sticks, all right? And you made these popsicle sticks the size of buildings, and you went 69 miles away with these popsicle sticks, and you tilted one of them 1 degree either towards you or away from you. You would not be able to tell which popsicle stick was tilted and whether it was tilted towards you or away from you. It's simply not a big enough discrepancy for you to be able to visually notice over 69 miles.
I agree, but then why can I notice the like curve of Earth like 2.7 miles away or 3 miles away?
Well, I don't understand.
The horizon.
Yeah. Okay. So as an object, if it follows the curve of the Earth, that once it goes beyond the horizon, it begins to fall behind it exponentially. Okay. So at first you'll see just slight covering the bottom. Before you start seeing it tilt away from you, you're going to see it start covered up at the bottom. At least from the surface of the Earth you will. So it's going to cross the horizon, and it's eventually, as it goes away, it's just going to block a little bit more and a little bit more and a little bit more as it leans away. You're seeing the effects of that curvature. You're not actually seeing it curve away from you. You're seeing the effects of it.
Okay, but if I can see the effects of it from like 3 miles away, then it's already curving at like 3 miles, and so that there's an effect so that the bot looks like it's disappearing bottom up. Then obviously if you imagine the Earth as a globe, it can't actually be that big, because if it's already curving by 3 miles and the Earth's meant to be like 24,901 miles,
No, the
it's
mass
like,
actually matches
how
completely
can it
for that
already
to be the
curve at
case.
3 miles when...
It's always going to be curving because the Earth is a sphere. But what you just said
But
about
then
the
when you
horizon
go
being
up,
a
why are
particular
you never
distance
looking
away
over?
matches the size of the Earth. The maths works out for that.
No, I haven't seen the maths for that, but like, obviously I'll take your word for it. But like, why can't we
It does
see, if
work
we
out.
go
I've
up,
done
why
it
can't
on
we
a few
see
of my videos.
over the horizon?
Because it's
why
in
can't
the
you see
way?
over the horizon. Yeah, the horizon's in the way.
We should
Like,
be able to see
how do you think
down,
shadows are
over,
formed?
like
How do you think shadows are
by the
formed?
sun,
Yeah.
and a
No,
solid
no. I
block
mean,
in the sun.
I'm not talking about like in a particular instance. I'm saying any shadow. How do you think it's formed? Because an object blocks the light.
Yeah.
So that's why we can't see
Back
over
in one
the
setting.
horizon, because we're inside of the shadow of whatever's causing light. In this case, the sun.
But what if you're about indirect sunlight? Then you can still see the horizon and things go over it, even with the sun overhead of you.
Well, because there's an obstruction. The Earth becomes an obstruction at that point.
But I find it weird that it's meant to be so big, but then the obstruction is so small, like 3 miles away.
No,
That's
that's
nothing compared to 29.
No. Okay, so the obstruction, when you say is 3 miles away, is only a consequence of your viewer height. That's an average of the average height of a human being. It's about 2 meters, so it's about 3 miles away. Okay, that has nothing to do with, with the shape of the... I mean, well, it has to do with the shape of the Earth, but that doesn't define what you're going to see if you take it lower or you take it higher. The actual shape of the Earth tells you where the horizon is based on your viewer height. So if you go up higher, then the tangent to the circle is further away from the point that you started at. All right, so it's basically what you could think of it as like this. Okay?
By tangent, you mean the straight line along the top of the Earth? Like if you would draw a circle, it would be the straight line across the top.
Exactly. It'd be a straight line across the top of the Earth. So if you were to take somebody and make them higher and higher and higher, you could actually make that line go further and further and further away relative to the starting point on the surface. And that's why with height, the distance to the horizon gets longer and longer. That's something a flat earther doesn't
So
know how
you'll
to
never
explain.
actually look down over the curve.
Well, okay, so
Because you keep going higher and higher and higher, and that tangent would keep horizontally out kind of thing. So
yeah, it
you'll
will
never
always,
actually
the
look
higher
over
you
and
go,
down.
the more percentage of the one half of the surface of the Earth you can see.
But
The
why
higher
would
you go.
the tangent get longer? Like, why wouldn't it bend down? I don't understand that.
I'm not sure I understand what you're saying.
Like the tangent line at the top of if we drew a circle and then we draw a tangent line and then we draw it longer and longer the higher we go up, why do we have to draw it longer and longer? Like, why can't we see over? Why? I don't understand why we have to draw the tangent line longer so that the horizon would be the same kind of thing.
Okay, I'm just gonna open up a thing to draw on and see if I can explain this. So give me 1 second.
Okay.
Okay. Everybody loves my artwork, my Paint 3D, so I'm sure you will too. Okay, so you have a circle, right? We're only gonna
Sell these.
We're only gonna draw like the part of a circle. Okay. So on the surface of the circle, here is, let's say an observer's here and we're just looking to the right, okay? On the surface of the circle,
Worst
this is the
circle
tangent.
ever.
Okay. On the shut up, y'all. I think I can hold
That's an even
shit
worse
down.
tangent.
Yeah, shut up. Fight. He's not helping. There we go. That was pretty damn close, okay? So, at the surface of the Earth, the tangent touches the observation point, okay? So now, if we go up, like to right here, we make an observation. Well, the tangent to the surface is like this. Okay? So now, from the surface of the Earth, everything behind this tangent right here was all in the shadow. Let's say it's the sun coming this way, or, an observation looking out this way. Everything here is dropping below the horizon. So if you have an object here, let's say, it will already start to be covered by the horizon, because the horizon is a tangent point on the surface. But over here to this guy, it won't even be close to the edge. And then if you go a little bit higher, then your tangent gets even further away. So then this one will be even, further away from the point at the horizon. And all these lines, while they don't look like it, they will all eventually cross the Earth the same way this one does, just come right up to it, touch it at one point, and keep going in a straight line.
But you don't find that strange that you don't look down over the curve?
Yeah, because that's how a circle works. I mean, you're not looking over the curve.
You just explained that.
Yeah, you're not looking over a curve. You're looking tangent. Yes, those. Oh my God, this right here.
I think this is what a lot of flat earthers struggle with, because, obviously, they expect you to be looking over the curve. Do you know what I mean? Over the ball, like.
Okay, but okay. So technically you are. Think of it relative to the observation on the surface. Okay, the observation on the surface you're looking above a curve, right? I mean, this isn't what they're talking about, obviously. They're talking about looking over it. But this is the original curve, is from that first point. The second point, you're looking over that curve. This whole area right here was curve that was originally hidden by that first observation, the tangent. Well, I know I should have used different colors. And then if you go higher, now you're looking over all of this curve. Yeah, I can't do that. Now you're looking over all of this curve that or down here. Yeah, I see. That's why I need to learn how to draw. So you're looking all over this curve that this guy can't see, but that this guy can see. So it is looking over a curve relative to another observation height, another viewer height.
But it doesn't look like a curve. It still looks straight.
No, really, it looks like, from an observational point, it looks like it comes up and then goes like this. And then when you're observing here, you're just looking straight. So it looks like it comes up.
Team, your drawings are so bad, I'm going to become a flat earther.
Yeah, right. I mean, you're still not looking. You're still not looking 90 degrees to the plumb. Okay, so if you had a plumb line that was hanging down, and you looked exactly 90 degrees, the Earth would not come up to your vision. Okay, it would drop.
So if we had a plumb line one side and a plumb line the other side, it would be a different. If we was measuring water, for instance, it would be different.
They'd be different relative to each other. They'd be different relative to each other, but they'd be the same relative to the local pull of gravity. They would both hang to the local pull of gravity perfectly. Yeah, actually, surveyors do that all the time. I have an observation I can show you that. I mean, it's a data set. It's not the actual observation itself, but I can pull up a data set from the 1970s where they performed this survey, and they got exactly what they were supposed to get, which was measuring the spherical excess of the Earth. Basically, when they have here you go. I'll show you real quick. I got this open already. We're just gonna do it. I don't even know how to erase shit. We're gonna do it like this. Control Z. I'm going to Control Z all the way out, guys. 1 second. Back to our original perfect circle.
I found some live footage of Team showing his drawings to his parents.
Oh, Stewie, it's wonderful.
This is going right up on the fridge.
Really? The fridge?
It's like we have a little Michelangelo in the house.
Okay, see you guys later.
I almost lost it when you said to put it on the fridge.
I know. I mean, what the hell is it supposed to be? A pelican or a school bus?
Looks like Muhammad Ali drew this.
What a dumbass. Oh. Hey, let's spit on it.
Yeah, that's how they treat me when I try to do art. And I try. Okay.
Oh, gosh. Oh, I'm about to cry. We laughed right there.
So let's talk about the three different. Let's talk about the three different shapes that the Earth could be. Okay, the Earth could be convex, concave, or flat. All right. Now, if it's concave, and this would be the top one, that would mean that these plumb lines are not. They point towards each other. Their commonality.
I'm
point
sorry
is in
to
the
interrupt you, but I really don't know what concave means.
The opposite. Okay. Think of it like if you're looking at a mirror. Okay, the mirror that is like a half bowl that goes away from you. So it's like kind of like it's caved in a little bit. That would be concave. And a mirror that was like puffed out towards you a little bit, that would be convex. So the Earth.
So you mean like curved away from us and then curved towards us?
Yes. So on the Earth, if you look at that, the Earth is the convex Earth, right? The concave Earth would be like the inside of this ball. So the surface on the inside of the ball. Okay.
So we're a convex Earth.
Yeah, that's where they come in. Okay. So look, we got to draw our plums, right? And this is what theodolites will do when they're measuring. Okay.
I can't see any drawing that you're doing.
Oh, yep, you're right. You're not missing anything. Okay. So let's say this is a theodolite. This is a person right here, and he's taking a measurement. He's looking at this person right here. Okay. So they both use theodolites. Now we'll get a extremely. Oh, I was almost so perfect with that straight line. Okay, so then they measure this.
Looks like the spiders had an epileptic fit and ran through some ink.
Okay, so
are they at the bottom of the Earth, being that the curve's like a U shape almost?
Yes, that's the concave Earth. Okay.
Okay.
This would be what a measurement on the convex Earth looks like, and this is what a measurement on flat Earth would look like.
Flat Earth.
Yeah. So when these surveyors take these measurements, what they do is they add this angle up. Okay. So they add these angles up. That's one angle.
90 degrees.
Yeah, that's two angles. So if angle 1, if the Earth is flat, what must angle 1 and angle 2 add up to be?
Well, they're both 90 by the look of it, but I'd say 180.
That's exactly right. 180. Okay. Now, if the Earth was convex, like it is here, that would be measuring this angle, 1.
Still 90 and 180?
2. Well, no. This time.
Oh, actually, no, it's a bit, actually slightly, didn't it? I thought it was straight up, but it's actually a bit of a slight angle.
No, yeah, it's a bit of a slight angle, right? Angle 1 plus angle 2 equals, well, would be greater than. What do
them fishy signs mean?
We're just going to call them angles.
I'm sorry, I don't know what the fishy signs are.
We're going to call those angles for right now. Okay. I just used alpha plus angle 2. Now I just did a straight alpha. Okay, 2 will be less than 180 degrees. Okay. So that's our three options right there. This measurement.
So one's more than 80 degrees and one's less than 180 degrees.
Yeah, one's greater than both of the angles would be greater than well, they don't have to both be greater than 90 because you could take them at different heights, but the summation of the two zenith angles will be less than 180 here. Okay? On the second one.
By zenith, do you mean straight up from the Earth?
Yes, exactly. Along the plumb line, the angle that you measure from the plumb line. On the globe Earth or the convex Earth, the two angles should always add up to more than 180 degrees. And if it's a flat Earth, the two angles should always add up to 180 degrees. Now, what do you think? This is based on surveying a world. It's everywhere. Every surveyor has to know this, right? What do you think the angles add up to always?
180 degrees?
Greater than 180. Close.
Why?
Because the Earth's not flat. The Earth's a globe.
Yeah, but like, if I look from one horizon to another, it's 180 degrees, is it not?
That's not what we're talking about. These are optical measurements. So, again, like when oh man, I think I just closed it. I did. Okay, so the measurement that they're taking is an optical measurement between each other, right? Then they measure what that, when they align the two theodolites, they measure the zenith angle on each side. And then they take the summation of those two zenith angles to determine like distances. You can calculate how far away something is, or an elevation of something if you know its distance based on the zenith angles. But it always adds up to over 180 degrees. And the further you get away, the greater this it gets over the 180 degrees. Which is exactly what you would expect.
I'm sorry, you broke up a little bit. The further you get away from what is 180 degrees, sorry.
From your measurement point. From one point to the next. So like you have the 2 points. So from one point to the next point, they will from one point to the next point they will they'll vary. Like if the points are closer together, they'll still be over 180 degrees, but they'll be just barely over 180 degrees. If the 2 points are 100 of kilometers apart, then they would be much greater than 180 degrees, like 190 degrees or 185 degrees. But give me 1 second. I'm pulling up a paper that was sent to me from Jesse.
I'd just like to say you guys suck because you debunked my density and I was hoping for a Nobel Prize.
It's all right. Let's see. I'm trying to find the one that oh, here it is right here. Okay. All right, one second. I'm pulling it up so you can see it for yourself. I'll put it on the screen for you. Okay. So these were the measurements that they were taking. I'm not going to go through the whole thing like step by step because I'm obviously not a surveyor, and this was just shown to me to show the data points and the actual measurements that were taken. But these were all taken from a unique point, and they were all taken to different observation points, okay, from the same point. This is the survey of the McDonald Observatory Radial Line Scheme.
McDonald?
Yeah, McDonald. It's
like food McDonald's.
Or McDonald's, yeah. It was a French fry.
Really?
French fry. No, okay, so these are the different, the different observation points that they took. And here is the actual sum of the reciprocal zenith angles. So as
Why
you
are there
see,
so many lines?
I'm sorry?
Why are there so many lines?
So many lines.
Okay,
yeah, right. Okay, I'm sorry. Yeah, I was looking at the data. Because they want to take more than one measurement. You always want to take more than one measurement so you can compare your measurements. The more data points you have, obviously, the better you can, the better model you can build for future predictions.
So what's that measurements of?
Okay, so right here, here's where you see the sum of the zenith angles, okay? So from observation point 1 to observation point 7, you take a zenith angle of one observation. You see how I said sometimes they can be less because of different elevations? Even if they're less, they'll still always add up to over 180 degrees. So, and the distance between the two objects should basically be spaced out versus the sum of the zenith angles as well. So what we could do is we could find, for instance, if we know that the second one is 1918, the sum of the zenith angles is 180 degrees, 15 minutes, 53 seconds for the first one, 180 degrees, 19 minutes, 18 seconds for the second one. So we can, if the model is correct, we can make the assumption that the first observation point is closer than the second observation point, and then we can test that out.
But where are you getting the times from?
This was it was done, let's see, I think it was done in 1977 right here.
No, but I mean, like, you said about the times. Where was the distance and the times done?
The distance
at the 180 degrees and the times.
That I'm not 100% sure what you mean by that.
That's okay, carry on.
Okay. Well, Yeah, if you can figure a way of rewording it for me and letting me know what you meant, I'll be happy to answer it. But okay, so the second relationship we see will be from the the distance between the two objects and the sum of the zenith angle. The sum of the zenith angle again will be higher the further the two objects are away, and you see that direct relationship here. Again, it's just to show you that the Earth actually does curve. Because if it didn't curve, we wouldn't be getting these measurements of greater than 180 degrees. We'd either get them at exactly 180 degrees, no matter how far away they went, or we'd be getting less than 180 if the Earth was concave.
I'm still a little bit confused.
We know.
Well, it's a science. I mean, there's it's a science, so of course, it's not something that's super easy. Even I don't understand completely the science of surveying. I'm still trying to learn it, but again, these guys have been surveying for years. They went to school for this. I mean, they're way more intelligent than you and I could ever be. Maybe not intelligent than we could be as a whole, but in that particular field, they shine over us, with their knowledge. So when you say that they're wrong, you really need to show how they're wrong. Because when I said, hey, I have a question about this, this observation that I'm about to speak about, I went to a surveyor and said, can you, kind of give me any idea about this? First thing he did was send me back other work from other surveyors who honestly probably didn't give a shit about the shape of the Earth. This was in 1977, before people were trying to argue about the shape of the Earth. Back then.
Don't worry about my partner down and don't care about the shape of the Earth either.
But the thing is that these are independent. This is independent of a bias. There wasn't a discussion that drove the observation. It was just surveyors doing their jobs, and this is the information they came out with. And you and I can speculate on what that data means. Go ahead.
But what about when Dell has been asking builders and things like that? Like I think his name's Dell. He goes around and he asks builders about the curve of the Earth and things like that in their vans, and they say no, they've never took any measurement with the curve of the Earth or anything.
Right. Well, okay. So when you're building something, okay, let's say train tracks. That's the biggest one that people like to bring up, because a lot of times train tracks are laid out in really long connections, long pieces. So how can they take the account in for the curve of the Earth? Well, steel bends. It bends under its own weight. So it naturally follows the curve of the Earth. The ground actually supports the weight of the steel. If the ground wasn't there, the steel would continue to bend down a little further. So the actual ground supports the steel's weight. That's how they can lay pipes out for long distances without taking into account the curvature of the Earth. Curvature of the Earth isn't even that great. We're talking about, like Fight said, 1 degree over 69 miles. That's huge for 1 single degree. So over 1 mile, we're looking at only 1/69th of a degree.
I agree, but why can we only see 0.04 of a degree? I mean,
that's the consequence
nothing.
of
We should be able to see more than that, surely. I mean, 0.04
well, of course,
of a degree,
if we were
taller,
we would. That's the thing about a sphere, is if we were taller, we would. If we were shorter, we would see less than that. We only see that amount because it's a consequence of the geometry based on the shape of the Earth and the size of the observation, the height of the observation.
So I understand that, but again, water doesn't curve. Like Dal showed a video with a bottle, and they could never get the water to curve, and it's always meant to be level to the ground. So if it was always level, Earth would be like an octagon or something.
So water and fluids in general they conform to outside pressures, okay? So if you don't have any pressures, there's no form water will take. Once you start putting pressures into it and accelerations into it, water starts taking on a shape, or fluids start taking on a shape. So for instance, when you pour water into a bowl, it takes the shape of the bowl because it wants to keep going down, but the bowl pushes up on it. The bowl holds it in place. It conforms to the forces acting upon the fluid. Now that begs the question then, when I let water come out of a hose, or if I just take a glass of water and turn it upside down, why does it pour out? There's no forces acting upon it. Why would it go down?
Well, I would have said it was more dense than the air, but you've basically debunked mine with the last video, so I have no explanation for that density-wise, so I guess gravity?
I mean, yeah, well, that's exactly what it is, because if you can even counteract the gravity. Think of this. Let's think of this, right? If let's say you put that cup on a string and now start spinning that cup over your head, right? Once you get that cup spinning with a certain angular speed, it's going to start the centrifugal force pushing out on the water is going to overcome the gravitational force pulling down on the water, and the water will not come out of the bucket. Again, if you're not spinning
flat Earthers have a problem with is angular speed and linear speed.
Yes, they do have a problem with understanding the difference between the two.
Because
100%.
I had a problem with that as well, so I can understand why they have a problem with that as well.
But yeah,
obviously now I understand it, but yeah, there is a difference, and I can understand why flat Earthers get confused about linear and angular speed because it's totally different.
Now think of this though. Let's say you didn't spin the cup fast enough to really overtake the acceleration of the water wanting to fall. What would happen to the water? It would fall, right? I mean, it would. You've taken it and tried to stop. I'm sure as a kid, tried to stop something you were swinging, and it just kind of went up to the top and fell straight down, right? I mean, that's the same thing that's always happening. That force is always present. And that force is a pressure. It is acting on the fluid always. So in all cases, in all situations, here at on the surface of the earth, you better expect the water to want to go down. Now, if you get something spinning in a circle fast enough to where it overtakes that force, then you don't have to worry about the water falling out. But that's because see, that's what I'm saying. Inside of your head, you accept that gravity exists, but you don't yet accept it because you haven't convinced yourself that it's there. But if you were to look at it in just the examples that I'm giving you and say, that force is always there. You know it's there because the moment that you stop spinning it fast enough, the water falls down immediately.
Well, I accept it's there because, obviously you debunked my density thing with that last link with the tinfoil and the gas, so that debunked it straight away because obviously it was more dense than the air, than the gas, but yet it still floated, so it didn't make sense.
Yeah.
So obviously it's not density; it must be gravity.
Well, no, that's a false dichotomy as well. If you only have density and gravity as your two explanations, then sure. If it's not density, it's gravity. But you yourself and me and fight and, all of us, we can't say for sure that is the ultimate last goal. I mean, we had to alter the way Newton thought about gravity because Newton's ideas only explain very classical situations. Then we had something that, or non-relativistic is what I should have said, non-relativistic situations. Then at relativistic situations, you have to have something more in depth, which is general relativity. So the idea that, if it's not this, it must be this. Well, no, that's not necessarily true either. It's just that's the best explanation we have until we have a better explanation, until we have a better...
But if that explanation works and that mathematics work, then obviously it must be true.
Again, it's true under a given set of laws, a given set of circumstances. So like when we were talking about, a helium balloon rising, that's given those circumstances, given the presence of an atmosphere, given the presence of acceleration that we can either call gravity or we can call driving forward in your car. I mean, either way it goes.
See, I thought a helium balloon would rise because it's less dense than the air, but I thought if you could in some way make the helium balloon a vacuum inside, then obviously it's still full. So that's why I thought it was density, but obviously it's not. So.
Well, yeah, and the way to think about that is to legitimately think, how would you, let's say you are a helium person and you're inside of a box, okay, and you say that you know from a helium experiment that you, the balloon person, are going to fall down inside of the vacuum, all right? So now, if they turned the box upside down, you would have no idea which way down was. Would you still fall in the same direction in the box, or would you fall in the opposite direction in the box? And the answer is you'd fall in the opposite direction of the box, because there's an actual force that's acting upon you and everything else, including that box. You there?
Yeah, I'm here. Sorry, you broke
Oh,
up.
okay. No, not at all. Not at all. All right. So is there anything else, Rachie, that you'd like to talk about tonight before we get out of here?
Or have we given you plenty to think about?
Her video is paused, so I think that she may be either getting a call coming in. She said something about taking a call or something. But what we'll do is I'll read off Super Chats here in 1 second. I'll give her a chance to come back, because I've seen some Super Chats that were actually directed to her, as well as weren't mean in nature. I've tried to be nice tonight, guys. At least a little bit nice.
Yeah. It's been a bit more of a civilized conversation.
But there's a difference between intellectual honesty and the disingenuousness of the majority of the people we talk to. Rachie's been very, very good in conversation. So that goes a long way in having a non-violent shouting match.
I don't want to share with you.
Oh, no, I don't know how much of that you caught. I was just saying I appreciate that. Not having to do that every time. But there's I'm about to start reading off Super Chats. Is there anything else you want to talk about before I move on to the Super Chats?
No, I think you pretty much debunked everything I gotta say.
Okay, well,
except for that water's meant to be parallel to the ground, and unless it was parallel to the ground, it would be like an octagon or a hexagon, you know, some kind of like diagonal shape. Like it shouldn't be curved like a perfect ball.
Okay, so the easiest way to think about that is to stop thinking of water as one object. Okay, water is a collection of trillions and trillions and trillions of tiny little molecules of H2O. All right, so they're independent from each other, even though they have certain forces that hold them together and keep them close and let them become like puddles of water and whatnot. They're still individual particles. So each individual particle is going to be influenced by the forces around it. So if gravity says that things are going to curve, let's say, the reason why it's like this is because gravity, the gravitational field from the point in the middle extends out radially, okay, spherically. So that, you know, from the distance at the center of mass in any direction is going to give you the same value, essentially, okay? So that's why the water will form at a gravitational potential that's equal around the Earth, all right? It should, without any inconsistencies. Of course, we're talking about a perfectly smooth Earth with a perfectly uniform gravitational field here. When you put water on it, that water is going to get to the lowest energy state that it can possibly get to. Each individual molecule of water will do that. And the state that will form is going to be in a sphere. And that's because the gravitational force goes out from a point in a spherical fashion.
Yeah, I still don't understand how it can be like curved and not diagonal, because if it's meant to be level to the ground.
Okay,
like
yeah, no problem.
So let's say.
Okay, so the distance. Let's take
But
a surface
it is
on
at every point.
let's take the Earth that I just said, the very smooth and spherical Earth that I just said. Okay, it's a perfect sphere. That means that every point is the same distance from the center. Every point along the surface is at the same level from the center of the Earth. And in this term,
so it was meant to be an oblate, not a perfect sphere.
Yeah. So that's why I prefaced that with, let's assume that it's just a smooth, perfectly smooth sphere with no gravitational anomalies or anything like that, because we do know that, you know, around mountains and whatnot, large areas of mass, we have a different gravitational acceleration. It might be a slightly higher gravitational acceleration in the direction of the mass. So,
but do you really believe mass attracts mass? Like, somebody showed me a flat Earth peer review. He showed me a video, and like I said to him, like, they only done it once. They should have done the experiment a few times and left it hanging a week or something, a few days or something, and like seeing whether there was any difference.
Do you happen to know which experiment this is?
It's something with like a pyramid. It's like a pyramid shaped object, and then they pull a ball underneath it, and then it shows like a gravitational attraction, so it shows that the weight increasing.
Oh yeah, you're talking about the YouTube video that me and Fight show off all the time. Yeah, that demonstrates that.
I ain't sure. I only just subscribed to you, so I'm not sure. And I only subscribe to Flat Earth.
Oh no.
That says
No, I'm saying Fight and I have showed this before, where the introduction of more weight underneath, more mass underneath, increases the acceleration. Therefore, it increases the force that the scale feels.
Okay, but then the thing, when you pick the scale up, it says like minus something, and then depending on which orientation you hold it in, the force changes. Like, so isn't it the same amount of force that holds it up?
I don't understand quite clearly the question you're trying to ask.
Honestly, I forgot. My memory's terrible.
Okay, so is there anything else you want to get to before we read off the super chats? Rachie, are you there?
Yeah, I'm here. I'm just saying, like, I don't understand how it's parallel to the ground and it still curves, like, because obviously it'd be like more of a hexagonal or an octagon.
Well, just every molecule, as you go along, is being pulled to the center of Earth. So the surface is naturally going to curve with the curve of the Earth.
But shouldn't it be like diagonal and then diagonal then diagonal?
Yeah, if they had length to them, if they had a length to it, yes, it would be like that. But they don't. They're individual molecules, so they just conform to that shape.
But then,
like
when
Play-Doh. Okay, tell me something. Can you make a ball of Play-Doh into a perfect ball, a roughly perfect ball?
Yeah.
No rubber. Yeah, but there's no straight lines on it though, right? On that roughly perfect ball. I mean, it's not like if you were to look at it real close, it's not going to be a perfect like octagon or hexagon or any kind of straight lines. It's just going to be rolled up into a ball. It's just going to follow each individual molecule of the Play-Doh will just follow the curve that you create with your hand.
Yeah, I agree with that.
Yeah, it's the same way with water. So the water will still end up curving and will still be attached without any kind of breaks in the attachment. It can still curve. It doesn't have to be perfectly straight. That's what flat earthers say. Flat earthers think that it must remain like the top of the surface of water will always remain perfectly in line with the previous point on the surface of the water, and that's never the case. That's never the case. It follows the pressures that are applied to it. So if you just talk about the surface of Earth, if you're talking about the ocean, the only pressure that's being applied is the force of gravity. It's pulling the air down on top of the water. It's pulling the water down on top of the surface of the Earth. This is why the pressure increases with depth.
See, I just thought the pressure increased because there was more molecules on it, like more weight.
Well, yeah, of course, but what's pulling that down on top?
Well, originally I would have said density, but you've actually debunked that, so I guess gravity.
But at the same time, instead of just accepting what I I don't want you to think that I know everything or I'm giving you the right stuff. I just want you to go out and see it for yourself. I think I've given you enough to question your original belief system. That's all I needed to do was show you how it can't possibly be density. At some point, you yourself will run out of options and will be stuck with one and only one option left, and that's going to be gravity. And at that point, that's the only time you should accept it, when you yourself say, there's just absolutely no possible way that I could ever think of it being something else other than gravity.
Yeah, I agree. I mean, you debunked me with that, so I can't exactly say it was density. So, yeah, it has to be gravity. Unless there's something else that I haven't thought of, it has to be gravity.
All right. Well, we're going to read through some of the Super Chats. There were some that were directed to you, asking questions. So I'll try to you can feel free to not answer or answer anything you don't want to, but I'm just going to read them out, okay? David Keller for $5 here in Wisconsin. All stores and building masks are required to wear 100% within 6 feet distance of each other. Wearing a mask is a good thing. Let me ask you something. Are you for wearing masks or against wearing masks?
Originally, I took my daughter out of school because I was scared of the coronavirus, so I would say I was for masks, but then I realised, I didn't realise, but some things say that the virus isn't real, so then I'm like, I don't know what to think, to be honest.
It's very
the virus
real.
is real.
Yeah, it's very real. There's a lot of
610,000 people have died from it.
Yeah, I was gonna say you would have to would you feel comfortable seeing one of those family members and saying, yeah, the virus isn't real?
Well, if there was actually there's nothing else wrong with them and they did catch some kind of virus which has problems with the breathing difficulties, then I would say yes, it was real. But obviously, because sometimes they die and they have cancer or some other thing anyway wrong with them, you don't know what to think. So.
Well, yeah, but
obviously, I don't know anyone who's got it yet. If once somebody gets it that's close to you, you realise whether it's real or not. But until that point, you think, is it or is it not?
No, you're right. You're right about that. There's been, especially where I'm at, we recently had a either 30 or 32-year-old man die because they all thought that it was not real. One of their buddies got tested positive for COVID, and they decided to have a COVID-19 house party to see who all could catch it and what would happen to them, because none of them believed it would do anything to them. I mean, they're strong, young, healthy individuals, 30 years old. Well, one of the guys died, and he told the nurse, hey, I made a mistake. And that's one thing I don't want to see happen to anybody. I don't care what your beliefs are. I don't want to see anybody get hurt. So
there was nothing else wrong with him and he just died from COVID, basically?
A lot of people are having that problem in America.
So when they go back to school in September, should I send my kids or not?
I would not.
Yeah.
No, I would. If they give you the option of schooling from home, I would just take schooling your children seriously and school them from home for the time being.
I kind of have to disagree with you a little bit there, team, because at least in the UK, schools are going to great lengths to make it safe for the kids to go back.
Keep in mind, over here in America, we're dealing with much different problem than some other countries in the world. We have hot spots in our country right now, which that's a good reason why I say don't send your kids to school right now if they give you a teach from home option. Definitely, but you gotta, at that point, it's on you to really ensure that your kids get taught right, not a system that's already set up for your children to learn. I wouldn't teach my children flat earth until they were adults. If that's what you believe in, I wouldn't push that on them, because it will keep them from being successful in the school system. But if I got the opportunity, if my child was in school right now, I'd tell him to just stay home, and I would teach him myself.
I totally agree with you. I don't tell my kids that I believe in flat earth, and to be honest, now that you've debunked me, I probably don't. But with the school and the coronavirus and that, I don't know what to believe. My mum knows somebody who actually works at a school, and they said they're not keeping the 2 meters distance, they're not wearing face masks or anything. So it's like, do you send them back or do you not send them back?
So I just looked at a study that showed that that Florida's population, I believe, of children under the age of, I think it was like 5 or 6. Maybe, let me see if I can find this. Oh, hold on. I think I do have it actually. I think I have it pulled up. I was doing research for a video, but it was showing the discrepancy between the number of children, the number of people that are of child age in the population versus the number of children who have tested positive within the group of people who have tested positive. And it was much higher. Like, children can catch this disease. Children can bring it home and can become vectors. And nobody ever questions them because they're always out playing and doing this and that. And, you know, they may not show a lot of symptoms to an adult who would normally be paying attention to themselves, you know. A kid he's out having a good time and having fun. You might not think, hey, I need to check his temperature, and he could be running a mild temperature still. So let me see if I can find that stat so I can at least read it properly. Okay, I will have to find the stat. But anyway, the basic thing was just saying that children are able to catch the disease. They might not have such a high mortality rate, but that doesn't mean that they can't spread it to other people. I would be wary if a school wasn't taking precautions with this. Just as a parent, I would worry.
Well, that's why I'm worried, because like what my mum knows, like the person works at my kids' school, but they're not doing the 2 meters distance or any face masks or any precautions whatsoever. But if you don't send them to school, then you end up getting fined and problems. You know what I mean? Like.
Oh yeah, definitely follow the law. I'm saying don't send them if they give you a viable option, like a teach from home option or an online option. That's the only thing I would be suggesting there. And that's just if you didn't feel comfortable with, you know, with the way that they were handling stuff. I mean, if they're handling it good, then obviously you can send them to school. I wouldn't run that risk myself right now. If my son's 20 years old, I don't have to worry about it. But if my son was 15 years old, I'd be telling him to
20 years old?
Yes, ma'am.
You sound young for a 20-year-old son, to be honest.
Well, thank you. I appreciate that.
Well, there was an accident with a contraceptive and some time machines.
Yeah, but regardless, I would just be careful if I were you when it comes to sending your kids back to school. Make sure you feel comfortable doing that for the safety of your children.
And you've thought on vaccinations?
Yeah, I'll be vaccinating myself and my kid when it comes out. I mean, my kid's old enough to choose on his own, but I asked him, and he said he would get vaccinated. Yes.
So my son's due some vaccinations, and I don't know whether to give him or not, because obviously you hear different things, you don't know what to think.
Don't listen to people who don't know what they're talking about. That'd be my first suggestion.
It's like you hear some people, and they're like, "Oh, well, there was talking, now they're not talking," or "Oh, there was fine, now they're disabled." And it's like, well, do I vaccinate? I mean, my first one I vaccinated, but she's meant to have autism, and my second one I don't know whether to give him his 3-year shots or not, because you hear that many different things, you don't know what to believe.
Well, I would say consult a physician about it, but it's probably in your child's best interest to get the shot, to get vaccinated. Now, here's what I want to point out to you. You see times when doctors step out of the crowds to do things for random strangers, right? I mean, they see somebody choking on the ground. You see a doctor come in and, do it. He can't use his medical skills to save a life. Now, why would you think that the same doctors that do this, the same doctors who put out the information about vaccines, who administer vaccines to children all the time, why do you think they would hold such a cognitive dissonance between the adults in the world and the children of the world? Why do you think they would go out of their way to save somebody they don't know, but infect a child, like save some adult that's choking on a piece of meat at a random restaurant, but And when they see a child, they think to themselves, that's a way that I could possibly cause a vaccine injury on. Doctors don't do that. Like, doctors have this oath, this Hippocratic oath is what it's called, to always do good, to always have the best intentions at heart. Now, not every doctor does that, agreed. But we're not talking about individual doctors who are trying to give their own individual vaccines. We're talking about the medical body here, the medical body that does what it can to save us as humanity. Has your children ever had measles?
No.
No, that you don't ever want them to get measles, ever. Okay, that's what the measles vaccine is all about. It's about saving them from that agony of what they're going to have to go through if they do get it, the scarring that might happen across their body that they might get, the possibility of death from that, the ability to pass it on to other kids in her age or adults who haven't been vaccinated before. That's the whole purpose of vaccinations, is to keep things from happening, just because one person gets infected. Because measles there are still cases of measles across the world. But because we vaccinate now, we vaccinate pretty heavily, measles is definitely been reduced as the measles in children has definitely been reduced. And I might be saying measles, I think I mean smallpox.
I was watching some people on polio, and they have to stay in an iron lung, which is like a device which keeps them breathing. And that made me think that I should get them vaccinated. But then at the same time, you hear parents saying, well, they got them vaccinated and then they stopped walking, or they ended up paralysed, or speech went backwards or something. It makes you think, you know what I mean?
Yeah,
should you do it or should you not do it?
Yeah, so, I was right. It was measles. It was measles I was talking about. Okay, because here's the thing. Polio was like, if, let's say one person in 10,000 people that are saved has an adverse reaction to the polio vaccine. Well, you can't literally go back and say, well, all 99,999 people should suffer as well because he or she or whatever the case may be was the 1 in 10,000 chance that you could possibly have an adverse side effect from it. So they weigh all this out. Is it better for humanity or not? If there's something that has a 50% reaction, like adverse reaction, they're not going to put that out on the market. I mean, the very first thing that's going to happen, look how fast news travels. The first thing that would happen is people be like, oh my God, look in this state right here. They just implemented this, and 50% of the people who took this vaccine had an adverse reaction. That would be the first thing that would happen on the news. You don't hear this. You hear individual stories. Why? Because individuals having adverse side effects are going to happen. Every one of us are different. So the vaccine can't be a one size fits all. It can be a one size fits almost all. And that's what they generally try to do with vaccinations, is they try to make it to where it benefits the most amount of people with the least amount of side effects.
Okay, but what about if that 1% or that one thing is your child?
Well, I mean, there's nothing you can do about it. I mean, what if your child catches the
child that would be alone, so.
I mean, I understand where you're coming from.
I know what you mean, the mass of the many is benefit of the one, but it still sucks, you know what I mean?
No, I agree. I'm not here to say that, that it's a good thing that, at least one person dies for every 10,000 that are saved. No, that's not what I'm saying at all. If I could have it my way, I would have it to where everybody was saved. But unfortunately, the way the reality works is we can't have it that way. It is something that, we need to get. When the vaccine comes out for COVID-19, I will be taking it. I'll do my responsibility, my part to play my responsibility. Or
you'll
play
take
my
it
part
even though those things say that what is it, Georgia limestone or something, say that they're only meant to be 500,000 people or something.
Georgia Guidestones, and what did it say? Down to 500,000 people across the world?
Something like that, yeah.
Who would benefit from that? Think about it. Who would benefit? 500,000 people. We're talking about 1/20th of New York City, right? 1/20th of the entire population of New York City spread out across the globe, who would benefit from that? The people at the top, what would they benefit from? There would be nobody to run the internet. There would be nobody to do the stock market. I mean, these people, they have lives too. They have lives they have to preserve as well. Why would they go out of their way to take away the life that they've worked so hard to preserve and just take it all away? Just destroy it? Because
I agree, but then
the Georgia
who wrote
Guidestones?
the Guidestones? Who, like,
well, there's
carved
a person who wrote it. There are people who know who commissioned the stones construction, or whatever you want to call it, but they won't give up the information. It's part of, I guess, the contract that they signed to create the stones. Part of that contract was the anonymity of the person paying for the stones.
Well, what about the Freedom of Information Act? Can't you get through that?
Freedom of Information Act, I believe, only applies to government stuff, and that's not a government thing. That's just a private citizen that put it up.
So it wasn't actually like anybody big, it was just a normal person?
Yeah, it's just a normal person. Or a corporation. They won't say who did it. They won't say who commissioned it, who paid for it. But they do say that there is somebody's name on record for who paid for it.
But they won't say who that person is?
Yeah, it's part of their deal they have with them, is they're just going to, like, the guy paid for them and wanted to remain anonymous. They said, okay, not a problem.
Do we know how old they are?
A couple of decades.
So not that old, so it could be somebody still alive now.
No, in fact, I can look that up. Let me see.
It's just making me wonder if it's Bill Gates or not, because he has a few things against him on YouTube.
1980. So 40 years.
So not that long then?
Yeah, not long at all.
I thought there was up like, I don't know, centuries.
Oh, no. Nope.
Hey, team. I'm going to have to get off now, dude.
Yeah, I'm going to go through the last super chats. Thanks, Fight, for coming on. Rachie, if you want to stay around for just a few minutes in case any of these super chats are for you. You don't have to, of course, but if you want to stay around, you're more than welcome to. Fight, if you have anything to say, go ahead and say it before you leave.
Always fun. Thanks for having me on, Rachie. It's been a decent conversation, and I'm glad to see that you've actually taken on board what we've said and kind of admitted that you were wrong about the whole density thing. That's awesome to hear. So thanks for the decent conversation. Everyone, make sure you like and subscribe, and check out my channel tomorrow for a debate, and then the day after for a new video.
Thanks for debunking me, by the way.
Glad to do it. Speak to you guys later.
All right.
See you later.
Speaking of which, Jessica G for $2. Team Skeptic wins. Flawless fatality. Flawless victory. Fatality. Yeah, I think it was a good conversation. Bella Charge for $5 New Zealand dollars. New Zealand, please change your name. We don't want people knowing we have dumb flirfs here. It's just embarrassing. Are you from Ireland? You're not from, like, New Zealand, are you?
Who, me?
Are you from? I'm not Ireland. I'm sorry, England. I don't know why I said Ireland. England. Are you from Scotland?
I'm from England, yeah. I'm from England.
Okay. Yeah. Okay. Good. I thought maybe Bella Charge's super chat was directed to you, but I think he's just saying that they've got flirfs in New Zealand. Oh shit. Bella Charge for $2. What ghost are we talking? Stretch. Stinky or Fatso? Do you know what they're talking about? Stretch, Stinky, or Fatso?
Yeah, it's the ghost from Casper, isn't it? Like the uncles.
Yes. Rangerman9404 for $5. I propose we make a new litmus test questions, like asking a flirf if they know what the speed of sound in a vacuum is. Do you know what the speed of sound in a vacuum is?
Faster than the moon's travelling, I know that because they're meant to say that we could hear the sound, but because in a vacuum we can't because there's no vibration.
Yeah, so the speed of sound in a vacuum is 0.
Yep.
For the reason you said, there's no particles in there to have a pressure wave. All right, Chrismer and
So
Dave for $2. What's that?
So you can't hear nothing because even though the moon's traveling at a faster speed, you can't hear nothing because it doesn't travel.
Oh, yeah, but okay, so that's a little bit different. That's wrong, and I'll explain why. Let's say you were in a car or in an airplane. Let's say you were in an airplane, okay? And you were traveling faster than the speed of sound. Could you talk inside of the airplane to somebody?
Yeah.
But you're traveling faster than the speed of sound.
No. Yeah, I'd say yeah, but I don't know.
The answer is yes. So the speed of sound is the speed of sound inside of a medium.
But they can still hear, but a lot faster.
Yeah. So when you're in the plane, No, you're right. You could still hear you because the plane itself is pressurized. So all of the medium on the inside, all of the air is stationary, except for the molecules bounce around, but it's stationary relative to the person on the inside. So when the person speaks, the sound wave still propagates through that wave at the speed of sound. And it'll only do this if you're separate from the outside world. Once you allow the outside world, once you're actually hitting the air around you is no longer stationary to you. Once it becomes stationary to the earth, then if you're traveling faster than the speed of sound, you couldn't make a sound. It just wouldn't propagate.
But I thought the air was always stationary with the ground.
Yeah, but then at that point you would be flying through the air at, faster than the speed of sound. So if the air itself is flying with you, then you're stationary relative to the air. If the air is stationary relative to the ground, then you're moving through the air faster than the speed of sound. So no sound could be made from your mouth.
Okay, I don't really understand this relative thing. So if I was on a train going 90 miles an hour and the car was going 60 miles an hour, what would the relative speed be?
What direction is the car driving in?
That we're both driving in the same direction, but the train's going 90 miles an hour and the car's going 60 miles an hour. What would the relative speed be?
Well, the car would be traveling negative 30 miles per hour relative to the train, or the train would be traveling at 30 miles per hour faster relative to the car.
So it's 30 miles per hour?
Yes. So basically, when you talk
proved,
about
the other person right. I thought it was 60 miles an hour, to be honest, because there's a 30 miles per hour difference, but they're going 60 miles an hour and then you're going 90 miles per hour, so there's 30 miles per hour. But somebody was saying to me via the reference, it was like 30 miles an hour.
Yeah, so you have to define what your reference point is. So if you say the reference point to you, let's say you're on the train, right? And you say, how fast is that car going? Well, if you're defining, if you're saying we're just going to make the reference direction directly ahead, for instance, then the car looks like it's traveling backwards at 30 miles per hour. Because
I didn't understand that. Somebody said that to me, but I didn't get it. I thought it would be 60 miles an hour still.
No, well, that's if you make the point relative to the train, it would be traveling backwards towards you at 30 miles per hour. If you make your point relative to the car, then the train would be passing you at 30 miles per hour. Either way, though, it's 30 miles per hour because they're relative to each other. Yeah, it just depends on what you make your observation point. All right, Chrismer and Dave.
I didn't get that at first, but it makes sense.
Chrismer, I can always draw a picture. I'm super good at that. Chrismer and Dave for $2. Wish me a happy birthday, damn it. Well, I did wish you a happy birthday, but happy birthday again, Chrismer. Thank you very much for coming by
tonight. Happy birthday.
Look at that. Even the flat earther is telling you happy birthday. JL Truth for $9.99. Is she completely missing that density and buoyancy are qualities of an object that determine its reactions to external forces within a particular medium? I believe that's kind of what we got at to tonight. I think that you were assuming just that density and buoyancy could describe everything, and that super chat was basically to say that those are only properties of a much grander picture. For instance, the sulfur hexafluoride and the aluminum boat, that demonstration. It showed that density and buoyancy was not the answer to the final question. There's a much deeper question, or at least a deeper question to be asked. The Hedgehog of Death. The Hedgehog of Death became a new member. Thank you very much, Hedgehog of Death. These emojis are for you, sir. Let's go ahead and do Nathan Thompson in jail, Victor the 5-star general, me and a mankini, and then 2 little dumpster fire emojis for tonight. Do you have your shirt yet of me and a mankini?
Who, me?
Yeah. Did you buy one of my shirts yet of me and a mankini?
I only subscribed to you today.
No, you have to check my Teespring out. I've got a shirt in there that with me and a mankini that says I'm Team Skeptic and I'm here to party. But it's just funny.
What, literally you?
Yeah, literally. If you
in a mankini.
If you can see the chat right now, if everybody will please spam the mankini emoji. If you can see the chat, you will be able to see what I'm talking about.
I can't see it, unfortunately.
Okay, I'll get it in here for you. Give me one moment. But all right, so hold on, let me show you, because it's gonna, once they start putting that in the chat, it'll go by real fast. Oh, there it starts going right there. And I'm gonna. All right, I got a picture for you. All right, here we go. All right, let me get it up on screen for you to see, and now you can see. That was me.
That's meant to be you.
That's not meant to be anything. That is me.
That's not you.
That is
yellow
me.
Thing like a Simpson.
Yellow thing like a Simpson.
It looks like a yellow.
No, that's me. That's me. I made a shirt because my chat loves to fucking harass me, and they made me do it. They made me make a shirt and a mankini, and I did.
Well, honestly, I thought you would mean some of the things I've watched on Fight the Flat Earth, but actually, you seem really nice.
Well, okay, so let me explain the difference between our conversation tonight and conversations in the past with other flat earthers. Other flat earthers are not intellectually honest. They didn't go back and look at how you approached the different things that we were talking to you about. You approached them with an open mind. Even if you didn't believe them, you approached them with an open mind. You didn't deny what I showed you and just say, because it doesn't match with what I say, I deny it, I deny it, I deny it. That is one of the hardest things to have a normal conversation with. One of the hardest types of people to have a normal conversation with. For somebody actually can have a positive back and forth adult conversation, I act like an adult, which is tonight. I'm acting like an adult because you treated me like an adult. I treated you back like an adult, and I think this was a great conversation. But I am an asshole.
I prefer you like this.
I am an asshole, though. It does happen, unfortunately. Okay.
I can understand.
It's all right. My reputation precedes me everywhere I go. Now people just go to watch me fucking shit on other people. So, Jessica G for $2. Rachie, it's not too late. Come to the light, love. I think you got a fan out there, Rachie. Jessica G's pulling for you. Angel Garay for $5. We'll get you there. We'll get you there. I'll help you there. Okay. I'll shine the light down the path you need to walk. And when you have a question, all you got to do is say, "What about this? What about this?" And I'll break it down for you. I'll show you where you need to go to see the answers for yourself, so you're not just trusting me, and you can do that journey on your own, and I'll just guide you and show you where to go. I would rather you not be a flat earther. Let's put it like that. All right, Angel Garay for $5. When I jumped out of an airplane at 20,000 feet, the air is lighter at that altitude. Why did I not go up? Which is a good question that you should ask, right? So remember when I was talking to you about both of us push on a ball with 10 newtons of force, right? So I'm pushing the ball at you, you're pushing it at me. We're pushing in exactly opposite directions at exactly the same force. The ball doesn't go anywhere. What ends up happening is, with the buoyant force, is the buoyancy at the bottom is pushing up harder. The buoyant force at the bottom is pushing up harder to support the weight of all the molecules than it is at the top. So if it's just buoyancy that tells you which direction you should go in, then you should always go in the direction that's not pushing as hard. I mean, think if you and I were pushing a ball and I pushed the ball harder than you and it came to me. That doesn't make very much sense, right? I mean, don't you think if I pushed harder than you, the ball should roll your way? Well, in the buoyant force equation, the same thing is going on. The bottom is pushing harder than the top. This is why a helium balloon rises. It's because the bottom is pushing harder up than the top is pushing down.
So I just thought it was about density, but obviously you've disproved that with the last link.
I mean, it is about density.
But I
to
just
an
thought
extent.
because it was more dense than all of it, then it'll fall down.
Yeah, but see, there's like, I'm trying to think of a good analogy to tell you. Like, a lot of the times people don't realize when they say, okay, well then it's just going towards the more denser medium. Then okay, well then if I go and I put a magnet or a piece of rubber up against a metal wall, it should never leave that metal wall because the metal wall is more dense than the air around it on all sides. So it should be stuck to
I know what you're saying,
the...
but most flat earthers would just say it's because the air immediately surrounding it, not just because the denser thing is to the side, like it's all.
Well, no, I'm saying let's say I put it up to where one side of a rubber eraser is resting against the steel wall, like your refrigerator. Let's say like a fridge door, right? The fridge door is more dense than the air around it. If I put a rubber, let's say a rectangular rubber eraser up against that steel wall, then the most dense thing around that rubber will be the steel wall or the refrigerator door, either way you look at it. It's still going to be more dense than all of the air around it. So why would it then fall down? Well, it's because
now you're saying it, I feel like it should go towards the door, but before I was thinking just because it's more dense, it should go down. But now you're saying it's kind of don't make sense.
Well, yeah. So that's the idea, is that it's really just acting. It's not a density thing, because if it was a density thing, then the density of the fridge door would play a role in the direction that the rubber eraser falls. But it doesn't have anything to do with it. It just simply falls directly down every single time. It's going to fall directly down to the ground. And that's because it's
But
gravity.
I still don't understand why that video of Flat Earth showed that thing going diagonal. I mean, you say it's the camera's orientation or something?
Yeah, sure. It's the camera's orientation. So let's say you were to rotate that video, instead of the thing falling at a diagonal angle, it fell straight down. Well, then it would make sense to you. You would say, oh, wait, he just turned the camera, which is that's all he did, is just turn the camera.
So if I turn the camera, it would be facing down, but before it was facing towards the wall.
No, he has the camera facing towards the wall, but he's turned it so that the pull of gravity is not straight down on the picture. It's at an angle on the picture. So
it's still gravity and nothing to do with any wind or anything.
No, it's just a trick of the mind, is what he showed you. He just showed you, instead of taking the camera like you would normally see the camera, he's twisted the camera a little bit. So now instead of falling straight down, it's falling at an angle. The idea is to say, if gravity doesn't exist, then no matter what angle you hold that camera at, it should always fall towards the denser medium, or it should always fall towards a less dense, whatever the excuse is at the time. We hear it all. We hear, oh, it falls towards the dense objects. Oh, it falls away from the dense objects. We've heard it all the time. So if you want to say, I think in what he was directly relating to was the claim that an object is going to go towards the more dense object, or more dense surface, right? The immediately more dense. So if you have an object and you say the air directly above the object is less dense than the air directly below it, therefore it's going to go down. Well, that's not necessarily true, because then we can go set it next to something that has more density than air. And by that definition, it shouldn't flow through the air. It should actually flow towards the object, because the object is more dense than the air. But it doesn't. It always falls in the direction of the pull of gravity, the local pull of gravity.
But I could have argued that, but obviously because the last link you proved me wrong, I can't even argue it.
Well, if you have any other questions or arguments, you're more than welcome to bring them back, and and address them with me or Fight or anybody else at a later time. All right, so let's see. Let's keep on going on. 1999 from Nerd Angle. Just another person that doesn't understand the science, so has replaced it with nonsense. A physics class would do you wonders. Seriously, be honest about doing research. Look outside of the echo chamber. I think tonight was your first peek outside of an echo chamber. I'm not saying that you intentionally find yourself there or put yourself there. I think that all humans naturally do that. We find a group of people that we can relate to and call us friends, and we call them friends. It makes it kind of easy to, to consider those people real close and believe in what they say and not even realize that you're sitting inside of an echo chamber. But when you come to somewhere like here and you are met with, a contradicting opinion, I think this was your first attempt, or one of your first attempts of looking outside of the echo chamber. And that's, the fact that you were able to take it in stride, I give a lot of respect for that.
Oh, thank you. It's not the fact that I was echo chambering it. Like, the only reason I thought of density was because I thought that's what it was, and then I searched Eric Debay. I searched, gravity is just density, and then I come across Eric Debay's video, which showed the levitating balloon, and I thought that was correct.
Yeah. Well, levitating balloon...
But obviously, I was wrong.
Yeah, levitating balloon it's a little different because you got to add the mass of the gas plus the mass of the rubber on the outside of the balloon, and that's how you get your density. And then you measure how much water it displaces, and you can determine from that point whether, what it does at that point. You can get a density. But all right, so let's see. Kick-Ass Dave for £5. The air above a balloon is less dense than the air below it. This can be measured. We have a pressure gradient. So why doesn't it go up? Which is exactly what I was just saying. Like, if you have one side of the balloon being pushed with 10 newtons and the other side being pushed with 9, it's going to move in the direction that the 10 newtons was pushing, and it will appear to only have 1 newton of force pushing it. This is because it's an addition of all the sum of forces acting upon whatever you're talking about. In your case, it was a balloon. So it was the sum of forces acting on the balloon. And what Kick-Ass Dave is saying is that the force pushing down on the balloon is less than the force pushing up on the balloon. So all balloons should essentially float, all of them, whether they're filled with helium, nitrogen, hydrogen, oxygen, doesn't matter. They should all float just because there's more force pushing up on them from the top or from the bottom than from the top. Stringer News, 1 for $5. Stay in school, kids. Mindless Googling is not a replacement for actual knowledge. Agreed. Nerd Angle for $4.99. What Stringer News 1 said. Agreed again with Nerd Angle. Fight the Flat Earth for $5. Rachel is wrong.
Love you too.
She's wrong. No, I'm just kidding. FTFE for $5. Did we just win? No, it wasn't. This isn't a competition.
Yeah,
of winning.
Fight the Flat Earth.
No.
I think you won.
This isn't a competition.
I can give you the trophy.
I want to say that if you stop being a flat earther, then it's society that has won. You've won for sure. I can count it as a moral victory, but society as a whole will have won because that's one less person that we're not going to have to take care of mentally when they get older. Because I don't think that I think you have a chance. Okay, I think you could do your own research and you could walk away with a better understanding of the truth, and you would also not be a flat earther at the same time. That's what I suggest, and I'm here to help along the way. All the way along. All you got to do is ask, say, hey, what about this? You can even be an asshole to me and say, fuck that. What about this? I disagree with this because of this. And I'll give you the best possible explanation I can give you to help you out.
Honestly, I thought you was a bit of a dick because you get mad at people, but honestly, you've seemed lovely to me tonight, so I can't even say that you're a dick.
I do get mad at people, but then again, they most of the time they give me a reason to be mad at them. I mean, I don't just go around looking to pick fights with people. I would prefer to have a conversation that lasts more than an hour and a half. But like the other night, the guy that I got into an argument with the other night, the first thing he did was start misquoting science. Like, he just said something that was wrong, and I just corrected him. I mean, I didn't, scream at him to correct him. I just corrected him, but he immediately took offense to the correction, started telling me to stay in my place until Fight the Flat Earth needs me, and I'm like, first off, he doesn't need me. Second, no, I'm not sitting there while you just say bad science. If you're saying bad science, I'm going to point it out. And again, when it was a feedback loop at that point, we just kept going back and forth. But thank you for being polite and lovely as well. Irish Demon for $2.99. $2.99 Aussie. A pig just flew past my window. A flurf? Admitting? Yes, I know. It's a rare occurrence, Rachie. A rare occurrence. Rachel O'Daniels for $5 Aussie dollars. I'd like to request she changes her name to something more appropriate, like Idiot. Well, I think
Idiot.
Yeah, Idiot would have been a decent name before tonight, but I think that you are open to the possibility that you're wrong. So I'm not calling you an idiot until you just deny everything we talked about tonight and start saying that I'm wrong. Then I'll say, like, okay, you're an idiot. I just went through
you're 100% right.
I went through a 3-hour presentation with you. You didn't come out with an understanding. Yeah, you're an idiot. But you seem to have at least learned something or taken something from this discussion. So not going to call you an idiot just yet. Robert Gassman for $5. The earth is round and gravity exists. What the fuck is wrong with you? And then Robert Gassman for $5 also says, I guess he is a dummy then. I wonder.
He.
Yeah, I don't know if they were talking about you, Fight, or me, but if it was.
Oh, I'm a man.
No, if he was directing it at you, he probably meant she. I guess she is a dummy then. But yeah, he's right. Earth is round and gravity exists. We can prove it. I'll also give you another proof. I'm going to tell you one thing before this night's over, okay? I'm going to give you one simple thing you can do at home with your smartphone, all right? And I want you to just think about it. Do it as a thought experiment. Look at what you see and then try to explain what's going on, okay? And I'll go over it with you before we get off. Bella Charge for $5 New Zealand dollars. Old boats didn't use GPS. They have things called maps. Planes used to use them, and I believe still carry them in case GPS goes down. Yeah, I think now they might use. I don't know if they use GPS. They might use GPS. I don't know if they still use the old radar systems or if it's strictly GPS now. It's a good question. JL Truth for $1.99. Why do you think MapsGo went out of business? Well, yeah, that is true. Are you old enough to know what a MapsGo is? Well, they may not have actually had it in England. Yeah. It's like,
no, I've never heard of it.
Back in the 30s, when I was just a young 30-year-old, we would have these big books that were bound on one end called MapsGos, and that's how you would get around the United States. You would drive.
I'm sorry, in the 30s.
Yeah, I know. I'm old as fuck. What you would do is
you're not in the 90s.
No. I was born in the 70s, so 70s and 80s. All right, but anyway, yeah, that's why MapsGo went out of business, because with GPS, we'd no longer needed paper maps. Great Circle for €5 or £5. I'm sorry. How can we land planes on the other side of the Earth? Glowing stuff on the moon? Not actually west? Total po. Now, do you know what a po is? Just out of curiosity.
No idea what a po is, although I've been called.
Okay. No. Okay. So I'll explain. A po is somebody who is holding a belief for an entertainment value. Okay, meaning you're not really a flat earther. You're just acting like a flat earther. Now, the one thing on this channel that we cannot stand are pos. Now, it's not that we can't stand them. Pos are funny, but it's when they come on here and act as if they're an actual flat earther, and then we're like, oh shit, you're just pulling our leg the whole time along. So please tell me you're not a po. I don't think you are, but you're not faking this, are you?
No, I was a flat earther because, like, obviously, to me, water couldn't curve and gravity was just density, but you disproved that, so I can't even argue that. Water's curving, I don't know if I can still argue that, but, like, obviously, Fight the Flat Earth done a video with the camera inside of a bubble, and he said there was no forces acting on it, and then when the forces acted on it, it act different, so that still makes me question things.
Yeah.
But like, obviously, you disprove my density being gravity thing, so obviously that's not density; it is gravity.
Yeah. Well, and again, before we get off tonight, I'll show you a little thing you can do at home and test this for yourself. Cool little experiment. And it's free too. Anybody can do it. You can show your kids if you want. All right, in Flat Earth for $5. Buy this girl a beer. She needs it. You did well. You did well tonight.
I've got vodka and Coke, thanks. Love ya.
What's your drink?
Vodka and Coke.
Vodka and Coke. Oh my God, we need to get you some whiskey. Get some whiskey in this woman's life. Commander Darklight for 50 Aussie dollars. Aussie. Your turn. Where you at? Rachie. Oi, oi, oi. Say that. Oi, oi, oi. I'll say it for you. This is the most civilized debate I've ever watched. Obligatory super chat. Aw, it should never feel obligatory, Darklight. You're my main man, dude. You and several others in this community. I love you. I love each and every one of you guys. You guys sure do make it an extremely, enjoyable event, and you put me in a position to be able to do this as a full-time job. So please never feel obligated, and thank you so very much for everything you do. JL Truth for $1.99. Nice. Don't need my atomic goggles for this one. Didn't need my atomic goggles. Oh, yeah, because we didn't go into a super dumpster fire. Rachie, are you still there? Because I can't hear you if you are. You may have muted your mic.
Yeah, what's an atomic super fire or whatever you said?
Oh, well, most of our, like you said, most of the debates are dumpster fires. So that's what he was saying. He didn't need his atomic goggles for this one because we didn't have a nuclear fallout here. Bella Charge for $2 New Zealand dollars. Go take a basic science course. Yeah, basic science courses would probably help you. And the good thing is, Rachie, is that it's never too late to begin to relearn, and it's free. There's information at your fingertips right now. Anything you have a question about, you can absolutely go find out on your own. And I know as adults, we kind of say, I've learned what I can learn in this lifetime, and I'll learn what I can moving forward, but I'm not just going to, excessively pressure myself to go learn harder and harder topics when I have family and job and all this other life to take care of. But going back to very basic science is something that anybody could easily go do on YouTube. You could go and get you a bunch of basic science courses, and not saying basic as in to demean you or anything, but just to refresh you on some of the concepts that they taught you in lower level education. Some of the concepts that as adults we kind of don't use every day, so we forget about it. We just move forward. So, yeah. All right, so let's go
I agree with everything with science, but the only thing was that I disagreed with gravity, but obviously you proved me wrong, so now I disagree with gravity too. I mean, now I agree with gravity too, shall I say.
Well, there's still a lot to be learned. Basic motion, laws of motion, and just natural sciences, I guess, things that, I would say sciences involving anything that you can do at home, buoyancy test, temperature test, stuff like that. You could learn so much from just going on YouTube and looking at some of the science courses that are offered for free on there. That'll help you get a better understanding of physics. Or Brilliant.com, who is not sponsoring this, but there's websites out there like Brilliant.com that has like educational courses for every level, every user of any level. So, all right. Bella Charge again for $2 New Zealand dollars. Where is Chesh? Bring on the boobs. Oh, I don't know if you know this or not, but I got one of my streams got taken down because I had this girl on who's a friend of ours, and she drew boobs on the screen. So they took down my stream because of her drawing boobs on it. It was an algorithm. Yeah, it was a complete cartoon boobs. Not even like, they were just two circles with dots that didn't even look like nipples. But I guess they were like, nope, cut them off, and they just cut me off like right there on the spot. But yeah, that's what he means by that. NANA for $6.66. Team forgot whistling. Team forget whistling. Get some drawing lessons. Do you have an issue with whistling? Can you do it? You suck almost as bad as I do, but you do have you're slightly better than me, but you're not great at whistling. I don't want you to ever go around and tell people that you're great at whistling, but you're definitely not as bad as me. So if anybody ever asks you, hey, can you whistle? Don't say yes, just say better than Team Skeptic can. Okay, here's my whistle. Let's see.
Show me a whistle.
I'm going to turn up my volume. Hold on. I'm getting there. One day real soon, I'll be able to whistle. I mean, you agree, right? That's whistling. Rachie, you've muted, I think. Are you there?
Yeah, I'm here. Sorry,
oh,
off
okay.
again.
Oh, no, not a problem. Okay,
Show
so
me
that was...
whistle again.
You didn't hear that? Oh, my goodness.
That sounds like wind.
Is it not wind? I think I need to put like a popsicle stick between the gap in my teeth. I think that might help.
Maybe licking your lips would help.
Hold on. Okay, they're supremely lathered. Okay. I suck.
Are you sucking in or breathing out?
That's how bad I suck, is that you can't even tell whether I'm sucking in or breathing out. I am breathing out there. Jeez. Thank you,
It sounds like you're sucking in.
Thank you, NANA. I appreciate you pointing out how bad I am at life. Bella Charge for $2 New Zealand dollars. Better watch out, Team Jessica. Or better watch out, Team Jessica will get jealous. Ooh, Jessica, where you at? She's ultimately my alien lover. She says I'm an alien, but she's totally in love with me. So she basically loves E.T. That's what we're going to say. Mitch Gardner for £5. Do we actually have a flat earther that is listening and learning? I need to sit down. Yes, Mitch, it was definitely a much more pleasurable discussion. Having someone who doesn't just scream at you and tell you how wrong you are and cut you off. Yeah, no. So see, you have people out there that are pulling for you. This is more than you'll ever get out of the flat earth crowd. Trust me. All right, JL.
Polite.
What's that?
I'm open-minded and I'm polite, so I try and listen to others' opinions and perspectives.
All right, JL Truth for $4.99. Hey Madden, where's Brett Favre in on that play? Or where's Brett Favre come in on that play? I don't know what you're exactly talking about, unless you're talking about the Monday Night Football game or either Monday or Sunday Night Football game where Brett Favre gets knocked out. And this is the reason they take helmets away from players now when they pull them out of the game for medical reason, because he just went and grabbed his helmet and ran back on the field with a concussion, ended up scoring a touchdown. One of the greatest moments in NFL football of all time. Love Brett Favre. Jessica G. Here comes the hate. All right, Rachie, be careful. For $10, aha, I got it, team. That terrible drawing was Photoshop crop circles intended to be disguised as a point. Wink, wink. I won't tell anyone you gave the mothership directions to Earth. Secrets are safe with me. Nobody believes you anyway, Jessica G. You could tell the whole world. Team Skeptic's an alien. Light doesn't interact with him because he's so skinny. End flat earth for $2. Hashtag save Rachie. See, I told you. They see it. They see that you have these opportunities in front of you. It's just what will you do with the opportunities? The plot hole for $2. Is this Crafty pulling a massive troll? Do you know who Crafty Keela is? If this is goddamn Crafty, I'm going to be pissed.
I've never heard of Crafty.
That's exactly what Crafty would say. Exactly. Okay. No, Crafty, she's one of our Irish people. You do kind of sound
English,
like her.
not Irish.
I know, and that's why I said earlier. That's why I said, why did I think Irish? And I was like, oh, because she sounds like Crafty, and Crafty's Irish.
I don't say I.
I. Yeah, we got another Irish fucktard coming next. Irish Demon for $2.99 Aussie. Just got prescribed medical weed for PTSD. So happy. I bet you are.
Oh, look at you.
Yeah, so jealous of you, Irish. TBP Aftermath for 100 Hong Kong dollars. It's so nice to have an honest interlocutor that seems to honestly want to learn. I'm gonna have to. Oh my god, I know I said that wrong.
Interlocutor. What's that?
I don't know. I'm about to look it up. Oh, a person who takes part in a dialogue or conversation. Interlocutor. Yeah, here we go. Hold on. Then I've got it for us. For anybody that wants to learn.
Interlocutor.
There you go. That's how you say it. All right. And yes, it is. It is so nice to have an honest interlocutor that seems to honestly want to learn. I'm telling you, it is the hardest thing in the world to get a flat earther that doesn't come in immediately says, no matter what you say, you're wrong and I'm right. So you are definitely an upgrade from that. JL Truth for $1.99. It's kind of the apocalypse over here. Yeah, I know, right? What the fuck is up with 2020, guys? Really? What the fuck is up with 2020? Sports are dying because of COVID. We have COVID. We have the protests and the riots. And we have a flat earther that's willing to have a conversation and learn something? 2020 is fucked up. Hands down.
What next?
Yeah, what fucking next? Exactly. All right. Cypher Zero, I'm sorry, I was looking at something. Cypher Zero for $2 Aussie. How'd the lip implants go? Can you whistle yet? Cypher, I think I answered your question about 5 minutes ago. Answer is no, and still. Well, actually, hold on. I can't judge myself. Rachie, can I whistle? And be as harsh as you'd like. Is what I do considered whistling?
I was expecting you to do an example, but now it's wind.
Oh, hold on. I'm trying to get it to be on that note for a long time. Was that whistling though, right? Please.
It sounds like I'm holding my ear to a seashell.
So seashells whisper then. I mean whistle then, not whisper. I heard air that time too.
Maybe whistling sounds like air.
You heard it here first, guys. It's whistling. No. Nope. Laughing my ass off. Yeah, and they don't agree. It's not. They say it's not whistling. It is whistling, you fuck faces. All right. JL Truth or Bella Charge for $2 New Zealand dollars. Rachie, ask the doctor about that. Not YouTube videos. Yeah, when we were talking about COVID stuff, never trust anything online when it comes to medical suggestions. Even when it's coming from me or someone else, unless they're a licensed medical doctor, it's all just talk. You should always take it as talk, including the stuff I said when I was talking about your should you trust going back to school or not. That's not really, like when I say I wouldn't, and that's on you, that all depends on your situation and what the doctors and medical people are saying and what they are referring you to do. Definitely don't listen to advice from me when it comes to medical.
Man, lucky for you, I trust you.
JL Truth for $4.99. Gardasil 9 is an HPV vaccine that has virtually eliminated cervical cancer that HPV causes if administered before HPV exposure. Yeah, Gardasil's a good one for vaccinations if you ever want to look at the actual stats. See, that's the one that all the anti-vaxxers are like scared of, is the Gardasil vaccine. And that's the one where they completely they just lied. They outright lied on that on their information that when they said that there was a direct link between autism and vaccinations. There is no direct link between autism and vaccinations. Before people were getting vaccinated, people were also becoming autistic. You know, I mean, it's like there's this correlation between the age that people normally start showing autistic symptoms, and that also correlates with the times when you're supposed to give people vaccinations. So for them to show up at, relatively the same time, they can show a strong correlation without having any causation whatsoever. Do you understand that?
Yeah, but the problem is, like, since I got my daughter vaccinated, she has actually become autistic and rocking and things like that. Like, so it makes me wonder whether I should.
Well, you know what? Actually, just to, I don't want to bring up personal stuff like that. So
yeah,
that just out of your privacy and your respect, I would rather not bring up all of that, because I'm not a doctor, and for me to make any comments like that would be extremely disingenuous, and it's not right for me to do that. So I would rather just like not talk about that. Not that I'm embarrassed or am trying to save anybody,
no, I
but I think you can understand
where you're coming from.
Yeah.
Like,
I just want to respect your privacy and your daughter's medical privacy. I think it doesn't need to be talked about on my live show.
100%.
Okay. All right, good. Bella Charge for $5 New Zealand dollars. She will go back to Flat Earth after seeing that mankini. And Jessica is now W3T, which, for those of you that don't know, spells wet. Oh, we love giving Jessica a hard time in the chat. The plot, but you know what? She fucks with me, okay? Just before you start feeling bad for her, Rachie, she fucks with me big time. She gets it. She deserves it. And she's got a super chat coming up. I know it's going to be something fucked off. Watch. The plot hole for $2. Someone get these two a plate of spaghetti. Aw, that was so cute of you, the plot hole.
Lady and the Tramp.
Yeah, I know, right? And now I'm trying to catch up on. Now I'm looking back on my super chats to try to catch up where I was at. And now it seems like I'm taking this long pause as if I'm contemplating whether or not I can afford a plate of spaghetti and a plane ticket to England right now. Stringer News 1 for $5. Everybody vaccinate your pets. Spray or neuter your kids. Something like that. Yes, something like that, Stringer News 1. Going to spay. Yeah, I'm going to spay or neuter my son tomorrow at the vet. Bella Charge. For $2 New Zealand dollars, we know you're going to show her a little thing. Look at this. See what they're doing to me now. Now they're trying to harass me. Yeah, Glass Monster for $2 Canadian dollars. The first time I did not want to yell at a flurf. You and me both, Glass Monster. Glass Monster's a good dude too. You and me both, Glass Monster. I truly appreciate that, and I'm glad that you guys are at least recognizing that she, put a little bit of intellectual effort into tonight's conversation. Let's see. Bella Charge for $2 New Zealand dollars. COD stream, Skep bitch. Yeah, most likely. Yeah, we'll do that later tonight, Bella. I almost hit you up last night for one because I got to catch up on my battle pass. Jessica G for $2. No, that was closer to a queef than a whistle. Excuse me, Jessica G? Excuse me. This does not. You need to go see a doctor if that's what this sounds like. Wow. Just wow, Jessica. Wow. I can't believe you said that in my super chat. I love you. You know how to make me turn red on the outside, Jessica. Huge arse for $5 Aussie dollars. That breezy sound you're making, is it coming out of your mouth or ... Yes, it's coming out of my
I know.
mouth. Exactly, but it is coming out of my mouth. But I don't know. Maybe if I tried to put it out of my other end, it'd sound more like a whistle, and you guys are happy and be like me and shit. Bella charge for $2 New Zealand dollars. Team wants to whisper sweet nothings in her ear. Jessica G's, no, I want to scream. I wanted to do like the scream whistle in her ear. Yeah, see, that was loud whistling. But no, I think that's actually Bella's talking about you in this situation. But that's fine. The Hedgehog of Death for $2. Let's see. It says Rachie, comma, I124Q. Oh. Do you see what he's saying? The super chat. Rachie, are you still there? All right. Rachie, I124Q from the Hedgehog of Death. So awesome for $2. I appreciate it. And TBP Aftermath for 10 Hong Kong dollars. My ears are bleeding. I don't know why. There was not much sound coming out of it. But yes, I think that's going to be where we end the show today. I'll give Rachie one more chance to come in and say her goodbyes before we close it out for the evening. It doesn't appear as if she's back, but I'll give her a few moments. Don't forget, this weekend we are going to have a live performance from a live jazz band playing during our breaks. I'm not sure what we're going to be doing, whether it's just going to be a live stream or I'm actually going to have somebody on for a debate. But there will be specific times when we shut things down, read out a few super chats, play some music for about 10 minutes to give the band, a chance to give everybody a restroom break, or anybody that's on the panel get a chance for them to grab something to drink or eat real quick. But that'll be either Friday, Saturday, or Sunday. I will let you guys know. Rachie, are you back yet? If you are, we can't hear you. I don't think she is. Oh, there she is.
Yeah, I'm back. I went to the toilet.
Oh, yeah. No, not a problem at all. Rachie, is there anything you'd like to tell the chat before we close this down tonight?
Yeah, thank you for listening, and thank you for Team Skeptic and Fight the Flat Earth for basically debunking me and proving me wrong and bringing me back to, I guess, gravity.
Well, like I said, there's some other things. Okay, but before you go, this is what I wanted to show you something, okay? Because I'm sure you have a smartphone, right?
Yep.
Okay. A smartphone has what's a built-in accelerometer, okay? It has 3 accelerometers, one for each axis, X, Y, Z. So what I want you to do, this would be your homework for the next time, right? I want you to get an accelerometer, download it on your phone. There's free ones. And I want you to just set it on the table and turn it on and see what it tells you. It's going to tell you a direction and an acceleration that you're traveling in, okay? Or the acceleration that you're feeling. So it's going to point towards the ground, and it's going to say 9.8 meters per second. And then I want you to set it down on its backside and watch how it changes. So it's going to rotate from saying the gravitational pull is down on the phone to back on the phone. And then I want you to set it up in landscape mode. And I want you to see how it swings down to the other side of the phone at that point. In fact, no matter which way you have down on the phone, it's always going to tell you that way is down without even knowing that way is down. Now, the scientific experiment doesn't happen until you drop the phone. Okay, so you're going to need some pillows and some soft blankets, or drop it on the bed. And what I want you to do is hold it above your head. And when you drop it, try to drop it so it doesn't twist, so it falls straight down. And as you drop it, I want you to look at it, or even record the screen if you can. And what you'll notice is that when it's in free fall, when it's falling, being pulled by gravity and nothing stopping it, the acceleration goes away. It'll read 0 acceleration. And the reason that you know this is because of that video you had Fight Show with the balloon. All right? When the car accelerates forward, you feel an acceleration in the opposite direction, right? Rachie, you there?
Yeah, I agree with you.
Okay, so when the phone is not falling, you just have one force pulling down. That's at 9.8 meters per second squared acceleration. When you drop it, there's going to be a force in the opposite direction because it's accelerating, just like in the car. When you accelerate in the car, you feel that pull backwards, right? Well, same thing is going to happen in your phone. When you drop the phone, you're going to have two forces competing with each other. One will be 9.8 meters per second pointing directly away from the surface of Earth. This will be because the phone is falling at is accelerating at 9.8 meters per second. The other is from gravity pulling on it at 9.8 meters per second squared in the down direction towards the surface of the Earth. Now, we already talked about it. When you have two competing forces acting in opposite directions of each other and they have the exact same magnitude, what is the force that acts upon the object?
Zero.
Zero. So when you drop that phone, if gravity doesn't exist, then you should see 9.8 meters per second squared pointing up. If you drop that phone...
Wait, I shouldn't see zero?
Not with no gravity. I'm saying, let's say gravity does not exist. Okay, if you want to verify that gravity does actually exist. Okay, so when you're holding the phone, it says 9.8 meters per second in the down direction. Okay, now the way that, let's say when you dropped it and you were just going to record the screen as you dropped it, as it accelerates towards the ground, if gravity was not there to accelerate it, you would only measure the acceleration opposite of the direction that you're accelerating in. Similar to the car. You accelerate forward, you feel the pull backwards. Same thing. As the accelerometer is accelerating towards the Earth, it feels a pull upwards in the opposite direction of acceleration. So it should measure that on the screen. So if you drop it and it says 9.8 up, then there's no gravity. If you drop it and there's a 9.8 meters per second squared going down, then they should cancel each other out and it should say zero. And at rest, when it's not actually accelerating, you should see the 9.8 meters per second squared showing the acceleration of gravity that's pulling on it. Any questions about that before we get out of here?
No, that makes sense.
All right. And I hear you have a little kid back there bleeding, so let's go ahead and wrap this up. Commander Darklight for 5 Aussie dollars. Great. Not a problem. Commander Darklight for 5 Aussie dollars. Great show, man. Customary super chat. Well, I do appreciate you, sir, Commander Darklight. And everybody else, I appreciate you as well. Thank you for coming out tonight. Thank you for participating. Thank you, Rachie, for having a good conversation and not getting overly upset about things. And not letting the people in the chat keep you from learning, because sometimes that can happen. And if you weren't able to super chat, there's not a problem. If you still want to support the channel, please share it on any major social media, Facebook, Twitter. Just go find a flurf. Find a flurf and say, watch this video. Watch this flat earther learn about gravity. Okay? Because we had a great conversation tonight. I appreciate everybody for coming out. Thank you to those who were able to super chat. And you guys have a great evening. I'm Team Skeptic, and I'm out. Okay.